then be part of a vector that you specify. So you could create 1, 2, 3, 4, and 5. And then here, if we look at this numeric vectors, you'll see the vector 1, 2, 3, 4, and 5. So vectors, they are list-like or array-like structures that store a single data type. And whenever you declare anything in R, at minimum, it would be a vector. So if I have vector 1, if I specify just one single value, even though it doesn't seem like a, can someone share the file? What file are you referring to? Are you referring to last week's file, Lennon?
Yes, I just joined, so I don't know like what platform you guys are working on.
Oh, so is this the first time joining the coding seminar?
Yes.
Oh, okay. So for last week and this week and the next couple weeks, I'll be teaching R. And so to get started with R, you can first install R, install R
Okay.
by going to here,
Okay.
download. Let me find you a better link. Give me one moment. Oh yeah, okay. So you could download R there, and then that's the programming language for statistical computing. And
Okay.
then the IDE that I'm using is R Studio. So this interface right here is R Studio, which allows me to easier develop in R. Otherwise, I'd be coding through the terminal. And for last week's notes, I do have that as well.
Okay.
And I will share that in the chat.
All right. Thank you very much.
Okay. So in R, even the most basic data types, they will be considered vectors, even though this doesn't look like something that would belong in a list or in an array, some sort of structure. Everything in R is going to be in some sort of data structure. So the most primitive data structure is this vector, and all of these primitive data types, like numbers, they will be also vectors as well. So here we can create a vector using the C function by manually inputting whatever values of data that we want into this function. So there are other ways to create vectors. We can create numeric vectors a bunch of ways. So one way we could create consecutive int vectors. Is to just use a colon separating the numbers that we want to have consecutively. So if I define this, int, I get the numbers 1 to 10 consecutively. And this works, doesn't have to start at 1. You could start at, let's say, 5 or something, 5 to 15. You can include negative numbers, 10, or you can also go in reverse. So this is, I'll briefly discuss last week. There are other ways to create numeric vectors. We might not always want to have it consecutively or consecutive integers. We might want to have different types of sequences with numbers. So we want consecutive numbers, but they won't always be, let's say, intervals of 1. We can do that with a seq function for a sequence. So to understand how the sequence function works, if you've never used it before, one way you can check out the documentation is to prefix the function itself with a question mark. Alternatively, we can use this help function with seq, and this will also work. And this will generate the documentation in this help tab on the bottom right, or wherever you have your help tab. So here, it gives me the information on how to use this function and also other similar functions as well. So for this one, I'm using the seq function, and it generates regular sequences for numbers. So I need a starting number and an ending number, and then I can have some other arguments along with it as well. So a lot of these are defaulted. So if I just run sequence, this does give me some value. It gives me a sequence with starting number 1 and ending number 1. So just a vector with the number 1 in it. If I put in some other numbers, let's say 4 and 10, or I guess we'll have 1 and 10, then it will give me similar to this consecutive interval. The interval will always be 1 if I don't specify any other arguments. So there are other arguments, parameters that I can change within this function that gives me more variety of sequences. So if I wanted to increase the interval to not 1, but let's say 2, I can specify this by argument and set it as 2. And what this will do is it will generate a sequence starting from my starting number, my from number, and then go by this interval. It always increased by 2 until I reach a number greater than my ending number. And then that's when I stop producing numbers for the sequence. So here we go by intervals of 2. The next number will be 11. It's greater than the ending number, so it doesn't produce that as part of the sequence. Another argument that can be specified is the length out argument. So here, this length out, if I specify length out, it should ignore the by argument, and what it'll do is it'll try to generate a sequence where the first number is 1, the last number is 10, and then you'll have however many numbers specified by length out. So this will only give me 2 values in this vector. It gives me the starting number and the ending number. If I change this value to, let's say, 3, it'll give me a sequence of 3 numbers. Where the starting number is 1, ending number is 10, and then you'll have evenly spaced intervals of numbers so that you have three total values in your vector. So the sequence basically just creates evenly spaced intervals. So what does the 1 at the beginning indicate? So because everything is a vector, 1 just signals the index of the first value on that line. So let's say I have a really, really long vector. So let's say 1 to 100. You'll see a bunch of numbers now show up at the output. So this 1 indicates the index of the value that first shows up on that line. This 19 means that this is the 19th value of my vector, or the 19th index, so that it allows me to easily search for whatever value at whatever position, and then if I need to retrieve those values, I can index it with that number. So yeah. Okay. Why doesn't your line work? It looks like it should work. Did you run the line of code? So to run the line of code, you either hit the run button or you hit command or control enter. So right now I'm doing a shortcut to every single time I go through this each line of code, hitting enter doesn't automatically run the code. I'm actually running a shortcut through my keyboard to execute the line through the console. So if I just hit enter, that creates a space, but you won't be able to see my keyboard. But if I hit command enter or control enter, if you're Windows users, then it will execute the line of code. So did you?
I hit the control and enter, but it just repeat the line.
And it doesn't execute it?
Yes, it doesn't show like what you have shown on the screen. Just repeat.
Oh, so wait, you're just saying this just repeats this, right?
In the console, yes, it just repeated and didn't.
Right. So
doesn't-
right. So this is in this line of code, what you're doing is you are assigning a value to a variable. You're not actually outputting anything. So because you're not outputting anything, nothing shows in the console. So if you run this line of code, you do have the variable defined in your environment. So this exists in your environment. You can now reference it.
Oh, so I need to.
After, right. So this doesn't have an output because you don't specifically tell it to print anything or return anything.
So
Well,
I need 2 lines, right?
Right. If you want to see the value, then you need to run it afterwards.
Okay, I understood. Thank you.
Yeah. Okay. So here we create easy consecutive vectors or consecutive numeric vectors. How do we do something similar with characters? For characters or consecutive letters, this will be a bit harder to do. So one way you can do that is to specify the characters manually. So you can do that manually by specifying the letters, all lowercase letters or uppercase letters. But obviously no one wants to do things manually. So how would we get a list of consecutive letters in R? Luckily, in R, they have some predefined variables for you. So here, this is a vector or a variable storing all the lowercase letters in the alphabet. If I wanted to create a vector of consecutive letters, one way I can do that is to index the values from this existing vector. So to index values from a vector, we can do so by specifying the position of the value that you want. Let me just, so this is lowercase letters and uppercase letters is just this in caps. So if I wanted to get, let's say, a list of consecutive numbers from here to here, one way to do that is to index the positions of values that I want. So if I wanted, let's say, the third letter in the alphabet all the way up to, let's say, the 6th, I can do that. Well, first, how do I get to the third letter? I can specify one value to return a single value back from the vector. But if I wanted to index more than one value, I can actually put in a vector to index another vector. So when I put a vector of numeric values to index another vector, what this does is it grabs me all the positions specified in this vector here. So here I am grabbing the third, fourth, fifth, and sixth index of letters. So it'll give me C, D, E, and F. So if I wanted to get the alphabets, we need to simply write basically you need to simply write the letters. Well, these variables are defined for you. So you can either simply write the letters yourself or reference an existing defined variable. So yeah, this is not great. So you don't have to worry about it too much. Most of the time, you're not going to be creating vectors of characters. It doesn't really make sense. It doesn't give you any data. Numbers are more likely. But this is just an example on how you could do something with characters as well. So more importantly than creating these vectors, if you're working with data, you're more likely to create vectors or creates more data from sampling other data sources. So how do we create a vector by sampling fake data or sampling data? We can do so. Let me add some notes here. So more likely than not, if you were to work with data, you might want to sample data from an existing data source. So one way you can do that is to use the sample function. So this function allows us to basically take a subset of values from an existing source of data or an existing vector. So if I wanted to sample, let's see, the first argument should be the vector or the data source. If I wanted to sample data from this vector of consecutive numbers from 1 to 10, I can do so by just specifying how many samples I want retrieved from this original data source. So this allows me to take 5 random values from this vector of 10 numbers. So if I keep running it, one thing you might notice is that none of these numbers gets repeated. And the reason for that is that in this sample function, there's an argument called replace, where by default, replace is equal to false. And this tells the function to sample without replacing the value. So if I select one number, let's say I select the number 7 from 1 to 10, that means that the next time I sample or pick a number from 1 to 10, I can't pick 7. I can't pick the same number or the same value from this vector. So one easy way to see how that works is if I try to sample more data than I have. If I try to do that, I'll get an error. I can't take a sample larger than the population, because if I don't replace the value that I just picked, then I'm going to get an error. So to allow sampling without replacements, I just need to specify replace as true. So now when I do this, you can pick the same number or the same value more than once. So if I pick a number from 1 to 10, let's say I pick the number 3, the next time I pick a number, I can still pick 3. The probability of picking each number every single time is going to be the same. All right. We could also sample from a distribution. So there are some convenient functions that allows us to sample from different distributions. So here, this is a uniform distribution. I can pick 10 numbers from a uniform distribution from 0 to 1. So if you look at the help for uniform, the default arguments, the min value is 0, the max value is 1. I can also select from a normal distribution as well, and I can specify the mean and the standard deviation. So let's say 10, this will select from a normal distribution. Besides sampling, I can also do repetitions. With the rep function. So this allows me to repeat some vector or some values however many times I specify. So the first value will be the vector storing the data, and then the second will specify how many times you want to repeat those values. So if I want to repeat number 0 10 times, I can do that. I can also repeat NAs, and I can also repeat whole vectors. And what it'll do is it'll just repeat the vector over and over again. But what if I wanted to repeat the values in a different way? Instead of having the entire vector outputted before I output the next, I want to repeat one value in the vector 10 times before I move on to the next. There are arguments to specify that as well, or to do that. So if I change the arguments to each for specifying how I want the values to be repeated, then it will repeat each value in the vector that I put in the first argument, however many times before I move on to the next. I also have, or there's also a length out argument, which length out, which limits the amount of data that gets outputted. So it'll follow the rules specified here or here, where you specify each or not. And then it'll cut down the output to just 10 or whatever values you specify. So it'll do the repetition in whatever way that you specify, and then it'll truncate the vector to fit the size outputted that you want. What if I wanted to repeat each value a different number of times? So instead of having each value in this vector repeat 10 times, I want to have a different number for each position in my vector. I can also do that with putting a vector as an argument after my data. So if I look at the rep function, this will be applied to the times argument. This will be applied to the times argument of this function. And what this does is it allows me to repeat each value a different number of times. So one important rule about this is that the length of this vector must be equal to the length of the data that you've inputted. So I can't do something like 2 to 1. This is invalid. And this is basically where you're plugging it in. Okay. Any questions so far? So now that we're able to create vectors, retrieving the data from the vector is the next thing I'm going to go over, how to retrieve Vectors. So to retrieve data, I've shown some examples of it. We just need to index the vector with some sort of position, so to retrieve data from a vector, just need to index it with square brackets, specifying the position of the values that you want returned to you. So did I say, let's just use letters. So for example, if I wanted one single value, I can specify the number 2. If I wanted more than one value, I can include a vector specifying the position of values that I want. So here, since I'm specifying a vector with the numbers 1 and 3, this allows me to retrieve the first and third positional value from this existing vector. When choosing data from a vector, you're not limited to only choosing the data once. I can actually repeat these numbers more than once, and it'll actually return the values over and over again. So whenever you put a numeric vector within these square brackets, it'll just keep getting those numbers, even if you've retrieved this before. So it allows you to use repetition to get the values multiple times. If you put in something that isn't a index, I think it'll just give you like NA or something. So here, 327, that's longer than the length of my vector, so there is no value at that position. This will give you NA. If you specify a 0, I think that will give nothing. That will be ignored. Yeah, zeros are ignored because in R, the indexing is 1-base indexing instead of 0-base indexing. That means that the first position is indicated by the number 1 instead of the number 0. Whereas in other coding languages, it's more common for it to be 0. So R also allows this very special rule for indexing, where if you use a negative number or more than one negative number, it's actually doing exclusion. So that means that if I put a negative number in an index, I'm grabbing every single number except that negative index position, except the value specified by negative. So I get all of the numbers except the third, or all of the characters, letters, except the third character, C. And of course, you can use more than one, or specify more than one, -5 or something, and they'll ignore all of the ones specified or prefixed by a negative symbol. If you try to combine negative with positive, I believe this will give you an error. Yep, that is. Error. And next. Nor 0. That's amount of range and NA. Negatives. Next. Okay. Besides using numbers to specify the values to be returned in a vector, it's very common to use a logical vector to filter out the data in a vector as well. So here I have the letters, and instead of using numbers, I can use a logical vector to return a vector where I'm indexing specific positions. So here I have a logical vector of true and false. This actually gives me every other character or every other position in this vector. So for logical vectors, if you use a logical vector, one important thing is that the length of the logical will have to be equal to the length of your existing vector. And if it's not, what will happen is that it applies the rollover rule to match. So here, because this obviously does not match the length of letters, this true and false gets repeated over and over again until you have 26 logical values in the vector. And for logical vectors, when you're using it for indexing, the positions where you have the value as true, that will be the positions or the data that you keep. And the positions where the value is false, that is the data that you ignore when you return the value. So this is why if I put true and false in the index, it will ignore every other character. So because of this rule, it's very common to use this to filter out values in a vector if they satisfy a specific condition. So for example, if I have a numeric vector from 1 to 10, I can filter out the data where the values are greater than 5. Or I can return values where the values are greater than 5 by creating a logical vector. Creating a logical vector storing true and false for if those numbers are greater than 1 and greater than 5. Sorry. So here, I have this numeric vector storing numbers 1 to 10, and I want to filter out that data to only keep the values where the numbers are greater than 5. So I can do so by creating a logical vector with true and false, storing if the value at that position is actually greater than 5. So I create this logical vector by comparing all the numbers in the existing vector with 5, and then it gives me false, 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 true, 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 and then use that back in turn to index the vector. So this allows for filtering data where it satisfies a specific condition. Any questions about that? So this is probably a more common way of using the indexing. If you ever want to filter data, it's not too likely that you'll index using numbers that you know beforehand for data. So this is very helpful for filtering out data so that you can focus on data that is important to you. All right. So the next thing I want to talk about is how do I overwrite values? So to overwrite values in a vector, basically you can treat it as a variable. Let's not overwrite that. You can treat a specific position in a vector as a variable. I can just reference it and then set it equal to some value. So I set it equal to 5. And then if I look at the numeric vector, I will have 5 instead of 2. And then this also works with selecting multiple values to overwrite. So if I wanted to overwrite the numbers 2 to 5, I just need to specify a vector of equal length to overwrite it. And then if I look at this, I now have 1, 5, 4, 3, 2, 6, 7, 8, 9, 10. All right. Another thing about vectors is that instead of having each position specified by a number, you can actually assign a name, a character label to index the positions of a vector. So if I look at the names of this numeric vector, there are no names assigned to it, but I can use this and assign some names myself. So let's just use the letters 10. And then if I look at the names of the numeric vector, it will, of course, give me some value. And what does that look like if I look at the numeric vector? You'll see that above each value, you'll have the letters, some letter assigned to it. And these letters represent the name for the position. You no longer see the square bracket 1 and the outputs, because instead of using numeric positions, because they have names, it'll just show the names of those positions. So now I can index where will we be using these? So the naming of vectors itself is not that important, but the idea of naming in positions and data structures do show up in tables. So if you were to look at a specific column of data in a data frame, the names of each one of those values in that column are actually associated with a row, right? And those rows may have names. So there are certain data frames or data tables that do have name values, which will be associated with a position. So overall, it's just a concept of allowing to name a position in a structure that is important, more so than being able to do it. So yeah, you might not do it if you were to create the data yourself, but if you were to inherit a data source from someone else, if you were to look at some existing data and they do have it, it is important to understand that this is possible and you can do stuff with it. Yeah, but for the most part, you don't have to memorize anything, just understand what the possibilities are, right? You're not learning it because you might use it, you're learning it because this exists as rules in R. And so it's better to understand more of their weird rules, I guess. So naming position of vectors. So now, instead of using a number to retrieve a value from this vector, I can now use a name or a character vector. So I can use specify a vector giving me multiple values. So one good thing about this named vectors is that the numeric indexes still work. This will still work, but you do have the other option of indexing by their names. All right. So this is one way to overwrite the existing names of a vector. All right, and testing. Uh, and to name vector. If you wanted to create the vector with the name, you can actually just have something like this. First, second, third. You can specify the names by prefixing it before an equal sign with the value that you want assigned to it. So this will create a named vector. And not all of them actually have to have names, which is a weird rule, but you can have these two positions have names and this third one not have a name. Very, very flexible rules, a bit weird, but this is possible in R. So before I move on to another data structure, one thing I want to talk about are conditional statements. So conditional statements are basically just the outcomes of, are basically just logical outcomes, true or false, right? So hold on. So in traditional coding language, conditional statements are basically evaluating if something is true, you do something. Otherwise, if it's not true, you might do something else. So the syntax for that is an if statement, right? So if you have a value as true, some value equal to true, I can do something, print true. So if I run this, if I have some value as true, it'll print true. If I have a value as false, it will not execute the code following that condition. So here, you see if F, you see the code printed, but you don't see the output. True. You don't see a value outputted. For conditional statements, it is very common to have a default outcome, which means that if the condition is not true, you automatically do something else. And you follow that up with an else statement. So if something is true, then you output it. Otherwise, you have this default value or this default code that you execute, which is printing false. If you wanted to chain a bunch of these together, the way to chain it is to use else if you want to have more than one condition evaluated. So let's say if false, if true, second, true, and then else print false. So here it will evaluate this, find out that it is false. So then because it's false, it moves on to the next condition, finds out that it's true, execute the code, and then finishes. It doesn't continue executing anything else or checking anything else. So this is the traditional syntax for if-else statements. But one tricky thing or one weird thing about R is that everything is a data structure, right? Everything, even the most primitive data types, the one I specify here, is a vector. It just so happens that this vector conveniently has a length of 1. So it makes sense for me to evaluate that value. But what happens if I try to have a conditional on a vector longer than 1? So let's say I have false and true. What do you think will happen? There will be an error because it's not sure which of these values to decide the conditional outcome. Does it pick the first value or the second value? And honestly, you probably want to have 2 different outcomes for each of these 2 conditions, right? So in R, the way that you evaluate a vector is not with the traditional if-else syntax. There's a function called one. There's a function called if-else, which allows me to evaluate each position in the vector and then give a different outcome depending on the values within that vector. So if I have, let's say, true and false, if the value is true, in that position, I want to return the number 1. If the value is false, in that position, I want to return the value as 2. And what this does, it creates a vector of equal length with one of the 2 outcomes, possible outcomes from checking the condition. So now I can evaluate the conditions of many values at once and then give a different response or a different outcome for each one of those values. So I can do something like if else, if the number is greater than 5, then I'll return the character big. Otherwise, I will return the character small. I can then do something or I can evaluate all of the conditions in a vector. And this is important when you're doing operations with large data sets, right? You don't want to evaluate just one thing at a time. You want to be able to evaluate all of the things at a time and have the execution happen in parallel. So this is a convenient way to evaluate multiple conditions at once. Okay, any questions about this? This is probably a bit confusing. If anyone has done any other types of coding, this might not be very familiar. But it's specifically because R is extremely focused on their data structures for managing data. This is a preferred way for doing conditionals. This is a vectorized conditional. All right. So the next data structure, finally moving on, is list. I'll talk a bit briefly about this. Similar to vector, to vector, because it's one-dimensional. But unlike the vector, it can store many different data types. So you're not limited to any primitive data type. You can store anything you want, even other data structures in a index of a list. But so to create a list, just need to use the list function, and we can create a list function or a list simply by putting whatever values you want inside of the list function, similar to the C function. And what it'll do is it will create a list storing each data structure or each data value in that position. So here, instead of using a single bracket, it's actually double brackets to indicate the position of a list. And that's because within a list, you can have other data structures as well. So here we have a vector inside of a list. So we can index that separately. Okay, we could also have named list values. So named something like this. And we can index the values in a list. Using either the double brackets for the positions or the name of that position. So yeah, lists you might not use too often. Just know that it exists and that it looks very similar to a vector, but it behaves very, very differently. If I wanted to convert a list to a vector, I can unlist the list. And then it will just create a vector. So then what it'll do is it'll deconstruct each data structure inside of the list and then pour it out into a single vector. All right. Moving on, I want to talk about data frames. This is probably the most or second most data structure, most important data structure after vectors. This is how most of the data that you would be working with would be stored in. This is tabular data, right? Things that you'd commonly see in Excel sheets or in SQL databases. You have two-dimensional data where each column represents a specific data type or a specific type of data, right? So we'll create a simple data frame. Let's say names call Alan, Bob, Cindy, David, Emily, something like that. We'll have a column for pets. I don't know. Zillow, bird, cat, dog, elephant. So yeah, we have name. Okay. So here we'll have a vector storing possible names and then a vector storing possible pets. And I want to create a data frame of, let's say, 1,000 rows of people with pets. I can do so by sampling from these existing vectors. So actually name sets, pet set. Let's do something like this. So this vector will represent the sets of names that I will pick from to create my data frame. Same with the pets. And I want to create a fake data set with random names and random pets in it. And in my fake data sets, I want to have 1,000 rows of data. So to do that, I can use some of the functions that we've gone over today. I can sample from the name set 1,000 times or n times with replacement. True. Names call. Do the same thing with pets. And then I can add other information, let's say ages. I can sample from 5 to 100, n times, replacement as true as well. And also incomes, I can say they'll only have an income if they're greater than 18, and then their income will just be their age times, let's say, what's a good number? 100 or something, or 1,000. So I now create all of these different vectors that are of equal length. I can stitch them together to create a data frame with this data frame function, which is incomes. And then if I look at my data frame, it's not great to look at it in the console. I now have a fake data set with 1,000 rows of data. Takes a while to load, but you'll see that there's 1,000 entries. And in this data sets, there are 4 columns. There's the names column, the pets column, the ages, and their income. So if I wanted to learn, so with this data frame, not all of the data types are going to be the same. Here you have 2 character data types, and here you have 2 numeric data types. If I wanted to get information about my data frame, I can do so using this str function. And this will give me the structure of an existing data frame. It'll tell me the number of rows or observations in the data frame. It'll just tell me the number of columns or variables in this data frame. It'll also give me a little bit information about each one of my columns as well. It'll give me the data type for each one, and it'll give me a sample of their data, the first whatever many rows that they can display. So yeah, in this data frame function, there's this argument called strings as factors. And by default, this is equal to false. But if I set this as true and then look at this data frame, I now convert all of the character. Here we have created the data manual. If we had already have the use that also, or how can, yeah. So if you, I will talk about it later about getting the data sets from somewhere else. What do you mean by how can we get that? Do you mean the structure? It's actually, what do you mean by your question? So to retrieve data from somewhere else, there are a couple ways you can do it. If you get the data as a file, you can read the data into R, and I will go over that. Another way that you can get data is to pull in data from, let's say, an API, basically just a web query. You'll request some data from some website or some web API, and they'll return you data, or you can directly query data from a database. So in R, there are functions that allows you or helps you query data from a database, and you can get data that way. So yeah, there's many ways to retrieve data into R. So I will be going over how to read data in from a file. That might be the most common way that you'll be working with data for now. But when you get into, let's say, industry, then you'll probably be querying data from a database or some sort of API. All right. Yeah. So back to factors. This is a special type of data type in R. And what it does is, if I set this as true, all of my character columns are now factors. So the difference between a factor and a character column is that factors are categorical. So here I have the pet set as 5 different animals. And in your mind, you might think, oh, there's certain values that can possibly belong into this category, right? You can't say an apple is an animal, right? But in the R code, there's no way to limit that. So if I wanted to, I can have any random value added to this set, and that will be acceptable by the code. But what factors does is it limits the options available. So instead of saying, oh, you can put anything in this and call it a pet, you are explicitly specifying that you have a group of categories, a group of values that form a category, and only those values are accepted. So let's work with a vector since it's a bit easier to look at. So let's say pet set 2, that's vector. So I have converted, probably would have been easier. I just did this. Okay, so I have 2 vectors, one storing pets as a character vector, and it will just show this right here, and one storing pets as a factor. So when pets are stored as a factor, you have these attributes called levels, and this specifies the possible values that can be added to this vector. If I wanted to, let's say, extend this pet set, pet set to, let's see, that's a pet set. I don't want to overwrite this. if I wanted to add to pet set 2, let's say add another animal, you'll see that that is allowed, right? If I add some value to the 6th position, it'll extend the vector and add that there. But what happens if I try to add a fox to pet set factor, this vector? It'll give me a warning saying that it's an invalid factor level NA generated. And so in place of what would have been fox, I get a missing value. And the reason for that is that factors represents a group of categories, and any value that isn't specified already as one of the categories will be ignored. It's not allowed. So for example, if you were to fill out a form and you were to a form about that includes your personal information, and in the states you put that you live in, you put some random place that isn't one of the 50 states or US territories, then those values will be ignored. Those are not allowed because that's not part of the predefined values in the category. So this is very important for limiting choices and to indicates that you have very, very specific choices that make up a group of, or that makes up a category. So one thing about these factors is that it also does save on memory as well. Instead of using characters to represent the factors, they're actually represented by numbers. And the numbers just represents the index for the levels. And so integers, they will save more space, more memory than a whole bunch of random characters. How does that affect memory? So if I look at the object size, this is something that you might not be too interested in, but so let's say headset 2, headset fact. You'll see that in the case of small amounts of data, the factor does use more memory because it stores level information. But once I generate large amounts of data from, let's say, 10,000 true. Once I generate large amounts of data, in the long run, the factors save a lot more on memory. And that's just because we're not storing every single character and repeating it multiple times. We're just using a number. We're storing the characters once in this levels, and then we're using numbers to represent that categorical value. So yeah, this is just a little tidbit. You guys probably should not worry about space saving stuff. All right. So yeah, this is how we manually create data frames. More likely than not, you're not going to be creating data on your own. You're going to be analyzing an existing data set. In R, there are a bunch of predefined data sets, and you can find them by running the code or the function data, and it'll list all of the data sets that you have available to you, or these are the predefined ones. Data sets can also data sets can also be defined in packages. So if you install some sort of package, you might have more data sets available to you. So one package that we can install is ggplot2. And this is how you install a package. Data sets. Also this. So this is how you install a package, install.packages, the package name. And then once you have that installed, you don't need to run the code again. Library gplot. To load up the package, I just need to run the library function to have the package exist. And then I can use data on the package name. And what it'll do is it will create the data frame or the table in my environment. So now I have this MPG data set available to me. And this MPG data set was defined in ggplot2. If you want to know about information about packages, vignette is a function that allows you to get package information or documentation. Packages. So it will give you a list of packages that you have available to you with their documentation. So if you run vignette ggplot2. Oh. If you run vignette and one of these labels, it'll tell you the documentation on how to use different functions and packages. So this documentation is more helpful for understanding how to use packages as a whole, whereas if you were to just use a function, you don't know how to use, if you were to just get the documentation for a specific function, you already know what you want to do. You just need to know how to execute the code. This documentation is to give explanation on how to use all of the functions collectively within a package together. But moving on to data frames, back onto data frames. With this MPG data set that is now in my environment, I can save this data locally on my computer by using a write function. So write CSV. CSV stands for comma separated values. This type of format is you can use and open in Numbers or Excel. It's just a format for storing tabular data. So write.csv, I can save the data in this table, this MPG table, somewhere in my local directory. Let's say dg.csv. And if I go through my Finder, go through my home folder, I will see that this file exists. And it'll just show up as some sort of spreadsheet. If I wanted to read the data, MPG2, from a file that exists on my computer, I can do so with a read function. So because the format is in CSV, I will use a read.csv function, and this will allow me to read. I imported the data set into R. Yes. MPG. Okay, so to import a data set into R, honestly, all you have to do is load up the library, and then you can directly call the data set this way. I know it looks a bit weird, right? But this is just how R works. I load up the library, which means that I can reference MPG. And if I put MPG into the data function, then it loads up into my environment. If I don't load up the library, I can also just specify package $2. I can load up the data set by specifying the package that I'm referencing it from. So a better example might be, let's say, so here, this tips I have not defined anywhere. How you imported the data set into R. MPG is what you call the file on your computer, right? So MPG is actually what's the variable defined by ggplot2. I didn't define it. But when I write the file to my computer, or the data set to my computer, I am naming it mpg.csv. But I can name the file whatever I want. It could just be, let's say, 1 or something, .csv. I don't even need the CSV part, but this will work. Back to how to load an existing data set into R. If a data set exists in a package and I want to load it up into my environment, I can just have the name of the data set and where it's and specify the package where it's defined. So here, this tips I've never used anywhere throughout my session, but this tips is a data set that exists in this reshape2 package. So once I run data tips and specify the package, it does load up tips into my environment. So have this accessible to me. What I'm doing here is once I have this MPG data set, if I wanted to apply any sort of transformation or analysis on my data frame and create a brand new data frame, I want to save my work somewhere. I can do that by saving it to a file, and I can label that file whatever I want. Here, I can label it 1.csv. And then later on, I can retrieve that data. So I've saved the data, now I retrieve it, and you'll see that the data is pretty much similar to the MPG data set. The only difference is that I have this extra column, and this column is just the index, the name of the rows that gets saved along with the data. So if I open this file, it has this column right here that represents the row numbers. This is the X you see here that is different from what you would see in the original MPG. Here, the row numbers are actually used as row numbers. So to get rid of that column representing row numbers, I can specify row names as the first column. And then if I look at it, I'll get rid of that. Or alternatively, I can specify not to include the row names. Two. Numbers are getting confusing. Here, this will work the same. So when saving the file, I can choose not to include the row names or not. Here, you'll see this column right here. And here you won't. Anyways, I want to quickly move on because we have a bit more to talk about about data frames. So in data frames, how do I now index data from a data frame? How do I get column data from a data frame? So let's go back to MPG. If I wanted to reference a column from a data frame, I can do so using this $ symbol. And this $ symbol allows me to reference an attribute that belongs to an object. So all these columns are basic properties that belong to a data frame. If I wanted to see the manufacturer column, I can do so with a heading column data. I can do so by using this $ and then the column name. If I wanted to get more than one column, getting more than column, I would have to use these square brackets to index my data. So the square brackets work similar to the square brackets in vectors, but the only difference is that I now have two-dimensional data instead of one-dimensional data, right? A vector is one-dimensional, it's a list or an array, but a table, a data frame, this is two-dimensional. How do I get more than one column of data from this index? So with square brackets, I can directly, I can't spell, I can directly specify a column name, and this will give me that column. But the output is a little bit different than what you see here. Here with a $ I output the value as a vector. Here with a square bracket, it looks more like a table. So this is actually a whatever many rows by one column table. This is a one column table where this is a vector. So whenever you square brackets with a column, you actually just get a data frame returned back. So if I wanted to get the model as well, I can specify more than one column, and it'll give me two columns of data in my data frame. So this square brackets allows me to select more than one column. So how do I, oh, actually. So this allows me to specify the columns that, this allows me to specify the columns of data that I want. How do I also select the rows that I want? So columns shouldn't be the only thing that I want to be able to specify when retrieving data. It's also important to be able to specify the rows, how to filter the data as well. So I now have a problem. I have two dimensions to specify, right? I have the row dimension and I have the column dimension. How would I be able to do that and specify values from both? Or even how do I just specify rows without specifying columns? That becomes a problem. If putting a vector within square brackets gives me just column data, where do I specify rows? So because a data frame is two-dimensional, when I add a comma within the square brackets, it allows me to apply filters row-wise or indexing row-wise or column-wise. So if I just run this, this does nothing. This actually just gives me the entire data frame. 4, comma, rows. So if I wanted to get, let's say, the first row of data, I can do so by just putting a number 1 before the comma. If I wanted to get the first row and first column, I can do 1, 1, or also, yeah, I'll just keep it like this. That was lowercase. I can specify both dimensions here by separating them with a comma. So I can select multiple rows of data. Honestly, the C's are not necessary, so let me just delete it. Oh. All right. If I wanted to get, let's say, the first 10 rows of data, I can do so by doing this, and then also specify however many columns I want. This one I'll just copy from here. So this format or this syntax gives me the flexibility to filter both by row and by columns. Okay. See, I mean, it's basically 10:30. So I guess I can stop here. Is there any questions about how to retrieve data from data frames? In future lessons, we will go more in depth about data frames. Everything will probably be focused on data frames. And yeah, I will share the file. 2, 2, 3, 9, 29. Um, two. So in all the following seminars, I'll mostly be going over data frames and how to manipulate data in data frames, how to create data visualizations. And next week, it will be a seminar on creating a dashboard in R. So a web dashboard in R. So that is quite interesting as well. All right. All right. So have a good day. If anyone has any questions, I can stay around to answer some of them. Otherwise, you guys are free to leave.
Hey everybody, this is Larry. This is day 29 of the Lico Day Challenge and a weekly challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm. It's a farm I haven't done before, which is always nice to see whenever I get a farm I haven't seen before. Hope everyone's doing well. Just another heads up is I'm going to at some point in the next month or two, I'm going to Taiwan and Japan. So definitely, if you're in those areas and you want to, just hit me up or go to Discord and chat on the server, and then we'll see what happens. Anyway, today's farm is a 96 monotonic array. I mean, array is monotonic if it's either monotonic increasing or monotone increasing. Is that grammatically correct? Or monotone decreasing. Yeah, maybe it is. I don't even know. And array is okay. So I think there are a couple of ways you can play around with this one, but I mean, this is pretty straightforward, right? You just try for decreasing, you try for increasing, and then there you go. You could also try for increasing and then reverse it because, if it's increasing, then reversing it will just decrease it or something like this, right? So one of those things. So you can definitely play around with stuff like that. And I think that's what I'm going to end up doing, even though the way that we're going to write it is going to be a little bit, I guess that's fine. I don't know. But yeah, if x is greater than y, then we return false. Otherwise, we do return true. You can actually even do this in one line, to be frank. And then now just return is increasing nums or is increasing reversed of nums, right? I wonder if this works. Yeah, that was what I was worried about, is that this assumes an array, but this doesn't, right? So it returns an iterator, which is a little bit. I'm just being lazy. There's a lot of random O of n things, but that should be it. Yeah, 1277, nice. I mean there's a lot of linear things here. Yeah, constant. You could do it in linear. Oh, sorry, you could do it in constant space for sure. The way that I did it is
Hi, everyone. Good morning. If you could give me a quick thumbs up that you can hear me and you can see my screen, it'd be great. Thanks very much. Thanks again for joining me today on the time series. So we have got let's go through this one here. We've got today we have got the first part of time series data. And then next week we have got the second part of time series data. So that is our plan. Anyone wants to share anything what what they think time series data is, or anyone worked already in time series data? I will give a quick summary of what I'm going to present for the next two seminars, so we can see if if that aligns a little bit. So anyone wants to share any experience in time series data, definitions, or what they're expecting? So I think first of all, and please interrupt me if you have got any questions. Please interrupt me. I can't promise you that I can answer all of the questions, but maybe we can have got a little discussions around it as well. So what I'm going to do is I'm going to work on my Colab notebook, and hopefully everyone has got a working Python IDE running for them. So I'm just starting with mine. So this is time series seminar. And today is the September 09, 29. So I will type everything in my notebook here, and at the end of this session, I will share that notebook. So everyone who couldn't or had got some typos or some problems to follow will get the full notebook. Let's just so my expectation is not that you have got already experience in time series data. So you start from the very beginning, and this will be our first part. The next part will be a little bit more advanced. So I will do a quick summary next week, but it will basically will continue from what we did this week. Let's see. What do I have got? So time series analysis. Why is time series analysis so important? Because it is basically it is used for forecasting. So if we have got any financial market data, you want to somehow predict how that financial data is going to continue in the future. So that's why we're using time series analysis. I will use a few practical examples to illustrate. So I have got some files prepared, which I will share on the chat, so we can work all from the same files as the data itself. And I will have got another example, which is a little bit, I think, at the end to summarize everything. Time series. So the first part will be, it is used for forecasting, but first we will look at different kind of time series. So we will look at random walk, we will look at white noise, we will look at some financial data and see what the differences are. So what we want to find out is what's the time dependency, are they stationary? Do they have got any patterns like seasonality in there in the data? And of course, what is there a trend in there? So we just comparing different kind of data series. In the second part, which then comes next week, is the forecasting models. So if someone is already aware of, some of you are aware of these ARIMA models, this is what we're going to discuss next week, and this will be implemented in Python. So let me just shut down everything so I don't get any notifications. But are there any questions? Any questions so far? I'm assuming that everyone has got their Python IDE up and running. Let's do a few more. Few rows in there. Hold on. I can quickly put in there notations. I have got some remarks here. You don't have to type them down. You will get the file afterwards, but I will put in the text file. Can probably copy this one in here. We have got certain notations. So time series variables are usually capital X and Y. The time period is T. The single time period is T. If we need to specify time x of t minus 1 will be a timestamp before t, and of course x of t timestamp of x plus, so one day ahead. We will use the following library. So let me see what we need. We need import, let's start basic pandas. We need SPD. We need NumPy as NP. We will need import matplotlib. So we want to illustrate it a little bit. Dot pyplot as PLT. So that's all the standards which we're usually using. We're also using for some graphs as well. We need Seaborn, SNS, and then we have to set it SNS.set. All right, we run all of that, and we should get all of our. It takes a little while, I think, in Colab. Did I put anything? Probably math. I have got a spelling error in there. Matplotlib. Matplotlib. Let's just copy it straight from there. And you can. It's a little bit tricky one where I always make mistakes on the spelling. Here we go. So math, M-A-T, okay, there's no H in there. Plotlib.py, pyplot as PLT. All right, so this is our libraries, and now I need to grab one file, which I will put in the chat. Let me just try to find it quickly. Here we go. And I will pull this one in the chat so we can all work off the same file. Just putting it in here. And it's called index 2018. So that's the index of financial data. I put it in the chat. And if you're working in the same environment as me in Colab, you probably need to upload it to have an example in this, in your directory. So I will do the same here. I will upload that file. 2018 over here, and upload them in your environment. There you go. Just moving it in here, and I have got under sample data. So all the others we don't need. I will give you another file later on which we need, but for the time being, we're just using the index 2018 file. And let's just upload that file. So let me upload that file. So we say raw CSV underscore data. That's what we call it initially, equals PD for pandas, read underscore CSV, right? CSV. And in my case, I put it under sample data. That's my directory, and the file is called index 2018.csv. Two W's in there. Let's see if that works. So that works. And then we do a copy of that. So usually what you would do is you're downloading it and then you're creating a copy as a data frame. So you say df as data frame, we call it comp equals raw underscore CSV underscore data dot copy. So we're just making a copy, which is usually a good thing. So we have got two data sets. We have got the raw ones, and then we have got the data frame comp, which we're then using to work with. And just very quickly is we just do a df comp. There you go. Dot head, and we just want the first 10 entries, and run this one so we can see here that's our 10 entries. So I give you a couple of 1 minute to just catch up and make sure that you get all the data. So that's the data we're going to work with. So give me just maybe a heads up or something if you need some more time. I'll just give you a little bit to catch up so you can upload the data, put it in your df underscore comp, which is our data frame, and that's what we're going to work with.
Oh, hi, Professor.
Mm-hmm.
Can you share the link again, please?
The link, it was a file.
Oh,
So I shared the file in our meeting chat, and you should be able to upload it from there. So all you need to do is download it in your directory. And then in my case, I actually uploaded it in Colab, and I used here on the side of Colab, I used the directory sample data where I put it in there, and then I read it from there.
oh, okay.
Let me know if there's any problems with the file, but hopefully everyone is able to see the file and is able to upload that file. Because if you can't upload that file, you will not be able to follow, because that's what that's what our exercise is based on.
Hi, Professor.
Yes.
Is the raw CSV data equals the DFCOMP? They are two same data frame.
Sorry, say that again. There was a little bit background noise.
I mean, is the DFCOMP equals
Yes.
the raw? Yeah, they are two same data frame.
So what we're going to do is first we read in the CSV file, which I provided, and we call it raw CSV data. And then usually what you're going to do is you're just making a copy of that, and you call that copy df underscore comp. So we just have got the raw file, which we always keep in the background, just in case we have to go back to the raw file. But what we're going to work on is basically the copy, which means df underscore comp.
Got it. Thank you.
All right. Anyone else has got any problems to upload the file? All right. So then we can continue. So what we can do is we can see the different attributes of that file. So with df underscore comp, that's our file, dot describe. And this will give us some statistics about our data set. So if we're running this one, you can see that in the file, we have got the SPX, so this is the S&P 500. We have got the DAX, which is the German index. Sorry, the DAX is the German index. The FTSE is the index from the from the UK, and Nikkei from Japan. So it will generate all of the statistics according to this column. So you have got in your file itself, you can see it here. You've got all the dates in front. You have got the different quotes, and you can see that, of course, they're all on different levels. So the first thing we want to check is, are there any NAs in our file? Because sometimes, especially in these files, you have got missing values, and then they're usually represented by NAs. So what you can do is you have got df underscore comp, And then there is a function called isNA. isNA, here you go. And this is part of pandas. And this will give us any NA. So you can see here that's a whole file. It says all false, so there's no NAs in there. But just to make double sure, what we can do as well is we can say that df_comp. And we've just picked one. So let's say that we've just picking out the SMP SPX dot isNA dot sum. So we're just summing everything up. The comma needs to go. And if you run that, we see 0. So what it means is it goes through the column of SPX. It checks if any of these cells are NAs, and then it sums it up. So if it says true, true is the Boolean true is also 1 as if you're summing something up. So if there would be one item which is true, it would come up as 1. Here we have got 0, and we will use this one later on when we're generating our calendar as well. So we checked, and currently there's no NAs in there. Of course, what we'd like to do as well is we want to see how the curve looks like, because it doesn't really help to see, the statistics. You can see, part of the data. A big part of time series analysis is usually visualize your curve. So I would do this one with df_comp, and then we concentrate currently on SPX, so our SMP 500, and say plot. And I played a little bit around with it. So what I would like to, the format I would like to see this one is you do a fig size, so that's a figure size, equals 20,5. So this is just basically the format we want to see that graph. We can give it a title, equals SMP 500 prices. And then depending on what kind of IDE you're using for Python, some of you need to do plt.show. So some IDEs don't need that, some of them do. So what I'm going to do, I think, going forward is I would always put plt.show in there. You might not need it, but I will just make it default, and it will show up the graph. So here you can see the graph itself. You can see here we have got the SMP 500, which goes from our 0 point, which is our first data set, to 6,000, so 6,500 or something. This is the number of our entries, and then here you've got the level. So now we want to play a little bit around. Let's see, we can do the same. Let's do the same. So we can copy paste everything just for comparison reasons. We copy paste everything. In this case, we're doing FTSE, FTSE. And then we can say that here, FTSE, FTSE prices. That should generate another curve. Let's go. And you can see here that looks a little bit different. It has got a different level. So it starts around the 3,000, goes up to 8,000. This one starts at about 500 and goes up to 2,700, I guess. So these are the two different curves we want to work with currently. We can do some statistics on that. So first of all, what we want to look at is in statistics or in time series analysis, we're looking around. It's like, how is our data distributed? Do we have got a normal distribution? So for this purpose, we need another library. It's called import SciPy. dot stats. That gives us statistics. And import PyLab. That's the tool we need. And what we can do is looking at our time series. We can have got log saying that SPCIPY, hold on, SCIPY dot stats dot probability plot. You can do a probability plot. The inputs will be, of course, our time series. So in this case, we say df underscore comp. Here you go. And which one do we want? We want SPX. And we want to plot equals PyLab. That's what we defined up there. We can put a title in there, plt dot title. We can call it SIP QQ plot. And as I said, PyLab dot show. We can run the plotting. So let's see how that looks like. So some of you might already have used the QQ plot. So what does a QQ plot means? It actually draws a red line. This is representing our normal distribution, and then it basically plots the market data according to that line. So we will see that for the majority, we will have got nearly normal distributed time series. But of course, here at the very end, you have got a lot of data outside there that distribution. We can do exactly the same with our FTSE, which we can pick up. So we can have got a little bit of comparison. And we say as FTSE here, and then we can say FTSE. And we can run the same thing. So here you can see that it has got on both tail ends, it doesn't really follow a normal distribution, which we would expect when we're looking at the graph. It's it's not really normal distributed from a time series point of view. So that's just very simple first view on our time series. So just to recap, is we saw that time series we plotted it on a graph, and then we had got log is would it fit our standard normal distribution, and then the next one is working a little bit more with the data. And what we're going to do is we want to put, as you can see up here, you've got all these numbers on the x-axis. So it would be nice to work with the dates, with the actual dates, rather than just giving numbers from the first entry to the last entry. So we need to somehow make sure that these dates, which are in our time series, so you can see up here, the first one is date, that it's been recognized as a date. Because later on, what we want to do is we want to fit these dates in a calendar. So at the moment, that date is doesn't mean anything. So you can see here, there is no date in there. It doesn't tell you the last or the first one. So we have to convert our first column into a date. So for this case, we say df underscore comp, and we're generating another column basically for our data set, and it's called date. So we call this one date, which gives us a new column, and we say PD, so pandas 2, and then date time. There you go. Date time, our input is df underscore comp dot date, and day first equals true. So that the date comes first. And you can say df underscore comp dot head. And we can have got a look how it looks now. So what we did is we generated another column. We overwrite the date, and then we gave it a date format. So the first one should be the a proper date format, and we can check that. So we can say df underscore comp dot date dot describe. There you go. So now we can see that it recognizes as a date because it says count, and then it says that the first date is 1994-17, and the last one is 2018-129. So it basically recognizes that what is our first date, what our time series starts, and what is our end date, where the time series ends. The next step, what we need to do is we need to declare the index. So the index should be our date. So we're setting the index by df underscore comp set underscore index. That's how we're setting the index. We're setting the index on the first column, which is a date. Let me just double check something. Let me just put one more step in here, just for comparison. And we say df underscore comp. So here you can see what I did is we just declared the date, and the date is in the date format. But you still have got the zeros until 6,268. So that's at the moment, that's our index. Our index is set to the first column, and it's just basically numbers. So if we say df comp set index, and then we set the index to date, and then we need to have got one instance where we say in place equals true. It's just one setting. And then we can say df underscore comp dot head. We can see in this case, our first column, which was here 0, 1, 2, 3, 4, 5, has disappeared. So now the first column is date, and we're recognizing that now our date is our index. So this is how we can work with. So let's see how this works with our plotting. So what we want to do is, the next thing we want to do is we want to see both curves. So we want to see the S&P, and we want to see the FTSE in one graph. And we should have got on the x-axis, we should have got the dates. So this helps us to actually identify, in a period of crisis, for example, you can exactly see where the graphs, going up or going down. So in this case, we do fig for figure, and then we have to declare, I said 2 axes. So what we need is, since we have seen up here, the two time series here, they are on different levels. So one starts at 3,000, the other one at 500. So it wouldn't necessarily make sense to plot them all against the same y-axis. You want to have got a y-axis on one side and one on the other side, so you can a little bit overlay them. So not is just cruising around on the bottom and the other one is far above. You want to see both of them just overlaying each other. So we have to declare axis. So axis 1 equals plt for plot dot subplots. So subplots, and we take the fig size equals 20 and 5. That's what we had got in the past. And now we have to define the axis 2 equals x1 tw I and X twigs. And now we can declare both of the axes. What I'm going to do is I say axis 1. So this is for the y-axis. X-axis is all the same. For the y-axis, dot plot. Is df underscore comp dot spx. And also what I like to do is I like to distinguish them with colors. So I give it a color. Color equals, and this is a little bit of strange. You can use any colors you want. I just picked one, so you do put the hash sign in there. I think it's 69B3A2. You can pick any colors. I just don't want to have them as the same color, so we can clearly see which graph is which graph. I do axis 2, same thing, dot plot, and df underscore comp, same thing, df underscore comp, dot, and now we need the footsie, comma, and color. We just pick another color, so you can, as I said, you can pick any color you want. I just figured out two nice colors. It's 3399 E6. That's just my color. So we have got the two axes. We need a title, plt.title. And we can call this one SMP versus FTSE. plt.legend should print that one, and it can say plt.show. That's all we need. Let's see if that runs, and then I can, here you go. I just pull it a little bit up so we can see everything. I leave this one up to you. So here you can see that I might need to add also which one is which one. So doesn't really shows which one is which one, but might need to have to figure this one out later on. But you can see now is you've got two axes on the left-hand side. That should be our, hold on, let me just check to 2000. That's our SMP. On the left-hand side, that shows you the SMP on the other side, the FTSE. And then it overlays, and then you can see here clearly 2008. Now you can see the crisis. You can see the crisis over here, down here, coming down here. That was 2003. So you will be able to, get an indication of how the market behaved when you're overlaying both of the index curves. And you can clearly see here, you've got the dates down there. So we have got the index as dates, and that's represented in our x-axis. We have got the y-axis, and it's divided between the two indices. So now we don't really, we can see that the data somehow fits when we're comparing them. But what we like to do is we want to set a frequency. So what we want to do is we want to see a frequency for business days. So there's a calendar behind it, and I can show you quickly a link. You don't have to. Let me just copy over that link where you can look up, and I can put that link in our chat as well. I just first showed the link. Here we go. And then I can put it in the chat. Here we go. So we can set a calendar, and the calendar will determine what days are we going to use. So for our purpose, we're going to use the business day frequency. So we want to have got every single day as a business day. And sometimes a time series doesn't have got all of the days, but we want to keep it consistent. So we don't want to have got gaps in between our time series. So for example, we created a time series, or we just downloaded the time series, and then we didn't get one day here, one day there, one day there. So what we like to do is first we identify which days or for which days the data is missing, and then we have to fill that data. So we have got a very consistent data set. So for this case, we can set the frequency. So we can say df underscore comp equals df underscore comp dot as frequency. So this only works when you already have got your first column, your index, defined as a date. So now what it does is it basically checks your date, your first column, and says that is that a business day? If that is a business day, then it will stay there. Is my next day a business day? And if there's a gap in between that, it will basically create an empty cell. If it's not a business day, then it will just kick it out. So as we saw here, we need B. So B is for business day. Here you go. And we can say df.com just to check. .head. And here we go. So here you can see that the dates are still very nicely in there. But now we need to check again what we did in the past is, do we have got any dates which now got included, which didn't really have got any data associated with that? So we're doing the same thing as we did before. So df underscore comp dot is na dot sum. We want to sum all of them one up. And now we can see that, oh, okay. So we have got, since the time series has got the dates in front, there's always the same number. So we have got 8. So we basically have got 8 NAs in our time series, which don't have got any data in there. So what are we going to do with this? Since we want to have got all business days represented, we have to fill them. And we have got, I think we have got 3 different kind of methods we can use to fill these NAs in our data set. So we can do front filling, so which fills it from the front. So from the date before that, so assigning the value from the previous period. So basically, if you have got one day, which is NA, you just take the date from before that. So you just basically writing over the day before that. You can have got backfilling, which is the consecutive day would be the same value, or you're just assigning a value which you put in there. So what we do is first we're going to do df, and we do it one by one. Comp, and in this case we do an SPX. So we do in the first one equals df underscore comp dot SPX dot fill NA. So it means that fill our NA numbers with, and then we can declare the method. And what I just described is we can do fffill, which means front fill. Front fill was basically assigning the previous number to the NA number. So we run that. I probably did I do F3 Fs? It's probably 2 Fs. Yeah, sorry. It's 1 F too many. Here you go. And then we can do the same as above. So we can copy this one down here just to check. And then now we can see that SPX out of sudden has got 0. So there's no NAs in SPX. So for the next one, let's try the next one, df comp dot footsie, which still has got 8 NAs in the time series. And we can say df underscore comp dot ftse footsie dot fill NA, and we're using the method equals backfill. hold on. Backfill. So here you go. And you can see now FTSE has got zeros as well. So whatever you use, it's it's pretty much up to you. You can use any number you want, and then now we can do the third part. The third part is basically with assigning a specific number to be included in the NAs. So we could do this one. Let's say we take the DAX, so fdf.comp.dax equals df underscore comp dot fill NA. And then what we need to do is we say value. So we're assigning a value equals df underscore comp dot dax. And then we want to write in every NA, we want to write the mean of the time series in there. So we say mean, and we can run that. So now we just determine the mean of the time series, and then rewriting it in all of the NAs. And we have got a little typo in there. Colors must be the same as the length. So at the end, the comp. Yeah, there's DAX. There you go. Here we go. So then we can run all of this again. And we will see that the only remaining one should be the Nikkei, which is still at 8. We don't really care about the Nikkei at the moment. So so this is to illustrate how when you're setting a calendar, so you want to have got a calendar that you don't have got any big gaps in your time series. And then if the calendar has got NAs in there, which can't be used when you're doing all your computations, you're just basically filling these NA with either with the front fill, with the back fill, or you're just picking up a value, which in this case was the mean of the time series, and just filling these NAs. All right, so any questions until here? Anyone? Everyone could follow?
Hi, Professor. I actually don't understand why you use the mean.
I mean, you could use anything you want. In this case, I thought that, if you have got missing values in your time series, you could use the mean. You could also use like the minimum, the maximum, whatever you prefer. But usually what I would say that is if you have got a time series of, let's say, 6,000 data points, and you have got, let's say, eight empty cells, which is NAs, I would say that probably if you're taking the mean of the 5,992 and put this one in all of your NAs, that would probably make sense and didn't cause any outliers. Because I think what you're trying to avoid is that these NAs, you don't really want to fill them with extreme values, because that's going to screw up your entire, analysis of the time series. So by replacing it by the mean, you will not have got any, strange numbers within the dates you're gonna fill in.
But why you use pre-fill for the FTSE?
I mean, as I said, it's completely up to you. It's it's just that what I want to demonstrate is that you have got these different kind of methods how to fill in these NAs. Because I think what a lot of people do is they're just taking the time series and they don't really care about the dates. So they could have got missing maybe a few days or even a week within their time series. And then if you're looking later on about how the time series, relies on previous days, that's going to screw up everything. Because if you're missing let's say you're missing an entire week, that wouldn't make any sense anymore, because you basically have got bits and pieces of these dates. So of course, if you're missing a week, then you might consider having an alternative source of your data set. But first, what I would recommend is get your data series and then look if your data series is consistent. Does it has got all the days? And in this case, it's a business days as a consecutive time series. And if you only have got bits and pieces missing, for example, on ours, there's only 8 missing, you know, it doesn't really hurt to just fill them in randomly with either with a number before that date or after that date, or replaced by the mean. It will not affect that much. Of course, if you have got bigger gaps, then you would need to find an alternative source.
I get it. Thank you.
No problem. So now what we like to do is we just concentrating on one data series. And so we have to simplify a little bit our data set. So we're still working with df_comp. If we ever need to go back to our original data set, we still, as I said, we still made a copy of the raw CSV data, so that's still there. So if you ever need to go back to that, we can always get it back. But now we're simplifying a little bit our df_comp, which looks like that at the moment. It's our data set. And we'd like to include the df_comp. We include a column called market_value. And this is going to be equal to df_comp.spx. So it's the same. It will copy SPX column and we'll give it a name called market value. And then df_comp dot describe. We have here, we have got a statistic, so we can see that SPX is exactly the same as market value. We just basically copied this one over. Now we want to get rid of all of the others. So we want to just concentrating on these market values. This is why I did the copy. So we can say delete df_comp. And now we want to delete all of the rest. So we say DAX we want to delete. We want to df_comp FTSE. We want to delete df_comp Nikkei. The nice thing here is if you're highlighting this, if you're forgetting your quotation marks, you can basically highlight that, and I think that's a collab thing, and it just puts it in the back on in the front. So if you, for example, I say SPX, I highlight SPX, and I press quotation marks, it will put them in front and in the back. And I think that should be it. I think. Let's see. df_comp dot describe. df_comp describe. And here we go. So we only have got one column left. So this is the market value which represents our SPX. For the time being, we just ignore all of the other ones. The only index we care about is a S&P 500. All right, so now we have to do another exercise, which we're probably going to use next week. So I'm just going quickly through this one, and I will repeat it quickly next week. But what you usually want to do is you want to have got two data sets. So you want to have got a data set for your training and for your testing data set. So somehow you have to split your data into two different parts. So one you're training with and one you're testing with on your time series. For this purpose, we just have to first figure out the length of our data set. So we know this one already, but let's just recap this one. So our size equals integer, and it's a length of df underscore comp. And usually what we're trying to do is we want to put a cutoff point. So you have got the initial data set and we split it in half. So you've got the beginning and the end. The first part you want to use as a training data set, which is usually 80%. So we would put here point times 0.8. So you take the first 80% of your data set as a testing, as a training data set, and the remaining 20 as your testing data set. Of course, in time series, you can't really randomly pick the dates, then it wouldn't make sense. So you want to have got, the trends and the seasonality you want to keep in there and not, just put in bits and pieces. So in this case, we say the size, and the size will be, in this case, for our 80%, will be 5021. And then, of course, the remaining one, that will be our testing set. So let's do df equals df underscore comp. And then we're using ilog from pandas. And we say that that's our training set. So the training set runs from the beginning to our size. So until our 80%. All right, so df, that's our data frame. And so we can say that df dot describe, just to check. And here we have got our data set, and we see that it's 5021. We can do another data set called df underscore test is df comp, same as above, df comp dot ilog. And this one is now from size to the end. So that's our remaining ones. So we run this one. We can do the describe as well. df underscore test dot describe. And here you can see that it has got 1,256. So this is the second part of our time series, which then will be our testing data set. We can do another one called df dot shape. That gives us, I think, the shape as well. Yeah, that's what we just verified. And we can do the same df underscore test dot shape. Is also, that's the remaining ones. So overall, this will be our complete data set. And now what we want to see is, we have got where one data series ends for, let's say, for the testing, you have got the for the training, you've got the testing ones right after it. So we can say that df.tail. So that's the last ones. And it ends with 2013 45. And then we can look at the other part. So df test dot head. That's where the next one starts. And this one starts right on the next day, so there's no overlap. We end these data series here with 13 45, and then it continues on the next one with 13 48. So this is just preparing our two different data sets. So maybe we use this one today, but I think for sure we're using it next week. So before I go on, any questions on that? All right, so we have got our two data sets, and now we can start with the time series. So now it gets a little bit more interesting. We've got an hour now done. We prepared everything. We have got our 8 data sets. Now we can start looking into our data set. So the next half an hour will be around seasonality, trends, if our data set is stationary. So we will do a few examples. And for these examples, we want to use the S&P, which we already prepared. But then we have got 2 more. So we can generate a white noise data set. So the white noise data set, just for comparison reason, it's just random. It's generated by a random generator. It has got, so the conditions for white noise, it has got a constant mean, it has got a constant variance, and there's no autocorrelation in any period. So we will talk about autocorrelation later, but what we have to keep in mind is it has got a constant mean and it has got a constant variance. So let's enhance our data set, which currently just includes our index, the S&P index, with the 2 other data series. So for white noise, we say Wn for white noise equals NP numpy dot random, as I said, random dot normal for the normal distribution. Location is equals df dot market value mean. So what we try to do is we let me just do this one here, did a typo in there. We're generating white noise, and we want to have got the white noise the same as the mean from our market value. So we can compare them a little bit. We don't want to have got a completely random one. So we're setting the mean for our white noise to the same as our market value. We're putting a scale, so we need to put a scale in there, equals df dot market value dot std. So what we're doing here is we have to give it a mean, our random distribution as white noise, and we want to have got the same mean as market value, and we want to have got the same standard deviation. So this is what we're setting it to, and then we need one more. We need size equals the length of, in this case, df. So df is our new data set, which includes all of the training data. Let's see if that works. Let's run that. So that worked. And now we can say df of white noise equals wn, which we just calculated earlier. All right. So let's see if that works. Yes. Here we go. So now our new data set df has got the dates, it has got the market value of our S&P, and it has got the white noise. So we generated the white noise here. What we can do as well is, did it work as we expected? So we can say that df dot describe describe. And here you can see that we have got the same amount. So the length is exactly the same. We have got the mean, which is approximately the same. And the standard deviation is not that far off. It won't be exactly the same as, you know, we're dealing with random numbers, but we can see that the mean and the standard deviation is very similar. So we have got the same kind of statistics, but of course we have got completely randomly generated data compared to our index data. So let's do a quick plot on that. So we say df.wn.plot. We run our fig size, and I usually stick to 20 and 5. We put a title in there, so we just know what we did, and we call it white noise time series. I put it a size in there. I think 24 look good, and plt.show, and here we go. All right, so here you can see that's what we generated. We generated our white noise time series, and it's completely random. You can see that, as we said, that you've got a constant mean, which is somewhere around here. So that's what we set it to. And you have got a constant variance. So let's have got a quick look at our other data set. So we say df.market value, just for comparison, the plot, and we take the fig size same as above, just to remind ourselves what it looked like. You can see plt.title, and I could do this one. I might do this one later on in one graph. There's prices, size equals 24, and we can actually do a y limit in there for the axis, goes from 0 to 2,300, so it doesn't goes into the minus or anything, and plt.show. But just to remind us a little bit on the time series for the first column, that's this one. And the third one, what we want is a random walk. And for this one, I need to provide you a file. So I generated a file called random walk, and I will put this one in our chat. Here you go. Because it's a little bit more difficult to generate that file, especially with the dates and everything. So I'm providing that file, and I will upload it in here as well. So sample data, I want to upload my file, and it's called random walk, and I upload that file. So now my file random walk is in my environment. I'm just double checking if I've got anything. Let's upload the file and see. Oh, got a warning here. Hold on 1 second. Flood warning. Maybe some of you getting the flood warning as well. I hope that the rain has stopped, but let's continue with our random walk. So random walk is generated by me in my free time, but then we can upload it and have got a look. So RW for random walk is a pd.read, of course, _CSV. It is in my sample data, and it's called random walk.csv. Random walk.date we want to set the same as PD dot to datetime time. So we want to align the dates, of course, RW dot date, comma, first day, no, day first equals true. So we're just aligning the dates. We say RW dot set the index is date in place equals true. That's exactly the same what we have done already above. And then we can say RW equals RW as frequency business dates. See if all of that one works. All right, you can quickly have got a look. RW.describe. Here we go. So we have got exactly the same dates as we need. And now we can put it in our data frame. So we can say that df, our data frame, has got a new column called RW for random walk, and it equals RW dot price. That's what I called it when I generated that file. All right. So then we can have got a look at our data frame again. df dot head. And here we go. So we have got now our data frame is consistent of our market value, which we did. We have got our white noise and we have got our random walk. So what we can do is the following. You're probably getting a little bit bored about my typing of the graphs. So I can copy paste this one in there. And we can speed it up a little bit. And I can give this code to you in the chat. So you don't always have to type everything. Of course, I like when you're typing things, but in this case, we're just doing basically the same thing again. So what I did is here we're comparing the random walk to the S&P 500. Random walk is a blue one, which just keeps going on like this. And our market value from our index is the orange one. So if you want to see the same, what I see is there's no analysis being done, but it's just visualizing the two graphs. So I can just copy paste it from our chat. So what we're going to do next is we assessing our three examples. We're assessing our random walk, our white noise, and our market value. And we can assess this one by doing a test. And the test is called AD Fuller test. So it's a Dickey-Fuller test, and it gives us indication of if it is a stationary process or not. And let me see if I have got a graph of stationary assumptions here. Maybe I can just copy this one over here. What do I mean by stationary data assumptions? I just flip this one over quickly here on my other notebook. So I need to share that one. Let me just go with this one over here and share that. So here's the explanation of a stationary data assumptions. The first one is a stationary data series. So you can see that, you know, the mean is exactly the same. So you can see the first period we selected is P1, the second period is P2. And then if you go on across, you will see that, you know, the period over period in time is the mean and the variance. So the mean above here, same as here. And then the variance between these 2 points are the same, or, you know, roughly the same. I mean, it's always like kind of like a measurement, which is not it's either or, you have got some kind of gradients in there. But clearly on the second one, you can see that a non-stationary time series has got also two periods, and one, the mean is up here, and one, the mean is down here. And even if you're looking at the variance, you've got a little bit here, and here you have got, these huge drop in here. So that's pretty much the difference between having a stationary time series or a non-stationary time series. So what we like to do is now we want to see let me just share back my new share, and we go back to the other screen. So we can go to this one here, we can say share, and we can go on to another screen and say that, okay, what do we expect? What do we have with our time series? Is it stationary or is it not stationary? So in this case, we need another library, and I will copy paste all of that. I don't want you to type all of this stuff. So I copy it in here, I run it, and I also copy it in our messaging box. So you can have got the same libraries. That's the libraries we need to be able to do this assessment. As I said, Dickey-Fuller test has got a lot of statistics, but the ones which we are mostly interested is, do we have got a stationary process or not? So we can say STS, which is our stats models, dot AD-Fuller, so Dickey-Fuller test, and first we want to investigate DF dot market value. So what do we expect? Do we expect this one as a stationary or a non-stationary? So I would say that if you're looking at the time series for the market value, we will see that it's not stationary. So if you're picking up in our graph here, picking up between, let's say, 1998 and 2000, we could pick up this period, and we're picking up, let's say, 2010 to 2011. So we clearly can see that for the market value for the orange one, or let's pick two other ones. Let's say 1996 to 1998 and 2002 to 2004. So we clearly can see that it's not stationary. We wouldn't consider this one as a non-stationary process. So let's run this one and see what comes out. So I did a couple of remarks here on my cheat sheet to explain you what all of the numbers mean. And you can definitely Google the stats library of the AD-Fuller, and you can go through all of them. So the first line is our testing statistics. That's not really useful for us. The second one is one which we're really interested in. So it's a kind of percentage. So it says 41%. And it basically means that, is that stationary or non-stationary? And what it represents is the p-value. So in this case, it says that it's clearly, it's what you call it, does not reject the null hypothesis. So it indicates that it is a non-stationary time series. So that's one here, and we will compare this one to a stationary one, of course, to see how that number changes. The third line is a number of legs of the regression. So next week we will talk about legs and regressions. So that will be an important number for us. The fourth line is basically just the number of observations. So we knew already that's our number of observations. And then you could see that from analysis, that's our 1%, 5%, and 10% of our distribution. Last line estimates, what did I write down? Estimates the maximum information criteria. We will talk about the information criteria, AIC, BIC, next week. So that's something to keep in mind as well. But for the time being and looking at this stationary ones, we're just looking at the second number. So that indicates 40%. So let's compare this one to DF STS. .ad folder, same thing. And we want to have got a look at our white noise. So white noise, we clearly know that white noise, as you could see here, should be a stationary process. You know, you can pick any, so the mean is all the same. If you pick the, you know, the deviations between two periods, it should be roughly the same as well. And this is how it's been defined. So let's see if that works out. Let's run that. And we can see that out of a sudden, second row here is 0. So 0 means it is a stationary process. Let's do another one. So we have got our market value, we have got our white noise, and now we can check STS dot random walk, STS AD folder df dot random walk, STS AD folder random walk. That runs. So in this case, it is also non-stationary, which makes sense. Is if you're doing a random walk, it always depends on the previous data points where it goes to the next. So it is a stationary process, and we can see this one here. It's like, you know, it has got a non-stationary. In this case, it is our blue line, and we can clearly see that, you know, you have got, if you take the period between 2010 to 2012 compared to 1998 to 2000, you can clearly see that there is a different mean and there's a different variance. So this is our first assessment. Now we can look at the second part, what we want to look today, and this is what about seasonality? Do they follow a certain pattern? And we have got a very, very cool library there. I think it's already, it's in our, I think in the library we used here, up here. So we don't need to upload another library. I think it's in our stats library. So let me go here and let me describe what I'm doing. So we just generate as additive. And we will go through the individual items later on, but I'm just generating analysis called deck additive. And what it does, it says seasonal decompose. So we want to do a decomposition of our individual time series and decompose it into different items. And let me do this one first, and then we're looking at all the different items we're decomposing it to. So you can say decompose, and we can say df dot market value. So this is what we want to decompose. That's our column. We say model equals additive. We will talk about this one in a second. And then we generated that. So of course we want to plot that. So our decomposition additive dot plot to plot that, and then plt dot show as usual. So let's see if that works. Takes a little while. And we did a typo error probably somewhere here. Let's see. Here we go. And this generating these kind of graphs. So first you can see here in the first line, that's your market value. So that's basically the graph, what it just plotted. Then it decomposes into trends, seasonality, and residuals. So you can see that the trend is probably the majority. So you can describe it as trend. It doesn't have got any seasonality in there. You can see by the magnitude of the numbers, it doesn't really show us anything. And you have got certain residuals, which are, quite small compared to the numbers. You're just comparing basically the y-axis with the numbers, where they go in here from 500 to 1500. The trend is usually most, so the curve is mostly described by the trend rather than by the seasonal, and there's not much residuals left. There is two different ways how to decompose that. So decomposing this one is basically you taking your market value and you decomposing it in trend, seasonality, and residuals, which can be additive, or it could be also be multiplicative. The same as above, so we can copy paste everything from above. We can just have got a quick look. And of course, this will be, let's call it multi. I don't want to write everything down. And and we say multiplicative. I hope I multiplicative. Hope I write this one right. Here we're saying the same as this one. And it's just a different way of decomposing it. So you've got two methodologies decomposing it. And here you can see that, from a multiplicative point of view, I think the residuals are next to nothing, and the seasonality as well. So this is our two ways of decomposing. I think this is a point in time where I probably gonna stop. We have got about 5 minutes, I think. First of all, any questions on that?
Hi, Professor. Why do we need to decompose it?
So what we want to find out, and this is a little bit going ahead of time, is let's say that I will take, instead of market value, I want to get, our RM. So we want to find out the seasonality, what our data series is composed of. And there you can see that, for example, you take your random walk, you can see that most of it is, do we have got any seasonality? And what I can share as well is I did another example, and I can share this one very quick. Is thanks for asking that. I prepared, and I don't run you through the entire code, but I did the same test on here you go, on air passengers. So there is a data set, and it is very illustrative. Is there is a time series which gives you the number of passengers, airplane passengers. And what you can see here is, you can see for the seasonal one, you can see how it behaves and what impact it has got on your time series. So of course, air travel passengers, they follow a certain pattern. They're following about holidays. They're following about school holidays, these kind of things. So what you're trying to find out is how much of my time series is due to a certain trend. So trend is usually, let's say that you have got index, like the market index, that probably follows mostly a trend. But does it also follow a seasonality? So if you're looking at, for example, commodity prices, then when you talked about oil, they do follow a certain seasonality because, of course, the demand on oil in the winter is probably much higher than in the summer. So in this case, it gives us another tool to look at the time series and lets us check, is there any seasonality associated with our time series?
Yeah, got it. And why do we need to use white noise?
So white noise and random walk is just for us a little bit of comparison. This is what I want to demonstrate on if it's stationary or not. So we have got, for example, we have got white noise, we have got random walk. White noise, we know it's a stationary process. So in this case, what I want to show is that how to read, how to read our test, our Dickey-Fuller test. To show you here on the white noise that it actually, the zeros here represents a stationary process. Any further questions? I can, in the meantime, I'm gonna save down the file and I provide it to everyone. So you have got something, if you come back, and I hope you're coming back next week, you can start off with that file. I will do a quick summary on that, but hopefully most of the students who turn up next week will have got that file available, so we can start off where we ended up this week. So let me just download that file and provide it on the chat. So any further questions, please let me know.
Is it when we try to split the data into trained data set and the test data set in the time series case, we only have to split it by the time. But I'm just thinking, why cannot use random sampling kind of?
Random sampling, you mean?
I mean, we split the data based on the time. So the trained data is always previous time, and the test data is always the later time.
Yes. So what you're trying to do usually is when you're predicting time series, you want to, of course, cover any trends you see in the past which might replicate. So if you would take random ones, you would take all of these, trends apart from each other, and it wouldn't be, you wouldn't be able to replicate that trend.
Yeah, got it.
What I'm going to do is I'm saving down 2 files. So depending on which IDE you're using, you have got either your Jupyter file, which is the first one, and I can also give you the Python file, which is this one here. So we are right on time. So thanks very much for joining. I hope you learned bits and pieces, and I'm looking forward to see you all next week. We're going through the ARIMA models. We're looking at auto regression. We're looking further a little bit, doing analysis on the time series we generated, and doing some forecasting. So I hope that was useful for you. And as I said, see you next week.
Thank you, Professor. See you next week, Marcus. Bye.
Thank you. Bye-bye.
Have a good day.
Thanks, Ben, for joining.
Oh, just call me. Very good.
Okay, so I'm gonna give it another few minutes so people can sign in. Looks like we have a nice little group, but David Romo, how long should I wait?
Maybe just 2 more minutes.
Okay.
Someone DM'd me when they would receive the Jupyter file, so I meant to reply directly.
Okay, I guess we can start. Let me go ahead and drop that file. It's a PDF. I'll share the full Jupyter notebook later, but it also comes with pictures, so we'll see how that works. There we go. All right, let's kick off. Thank you, everyone, for joining. My name is Chris Mann. Yeah, I should have put that as Chris Mann instead of Christopher, but that's my legal name. So yeah, you can see here I've got a background in physics, and I switched over to finance in the mid-90s and got my PhD from NYU. At the time, I was much more focused on investments and portfolio construction. At this point, I've derived the CAPM from first principles so many times I can do it in my head, which is silly. But I randomly fell into doing credit risk. First in my PhD, where I wrote a couple of papers on corporate bonds. And then when my first job ended up being at Moody's, which is a credit organization. So, and I've basically done almost all there is to do in credit, whether it's securitizations or consumer or wholesale. So, fun fact, my biggest problem in my life is trying to get my brain to stop working because it runs very fast all the time. And so one of the things I found that helps me fall asleep is I literally will choose a hard math problem, because what will happen is it will chase out everything else I'm thinking about until I can just fall asleep. So sometimes that backfires because I might actually solve the problem and then I get excited and I wake up. So, but that does happen. And then so that I can get some benefit from association, one of my PhD advisors, Rob Engel, was nominated for the Nobel Prize and was actually supposed to go to Stockholm during the same month that I was going to defend, and that might have delayed my PhD by about 6 months. Luckily, it didn't. This picture is from a trip to Spain. It's from the Alhambra. The Alhambra was a palace of the last sultan in Spain. I love this picture because you look at it and you look through it, and it's so beautiful out there with the trees and the buildings, and it just shows promise. And I think that is a good motive, good motif for today. Today, we're going to talk about how to create a bank failure model. And it's, to me, it's a fascinating world, not just in creating the model, but as you go through the steps to create the model, you learn so much about the banks themselves, how they run, how they are run. Sorry, if I sound a little off, I was at my wife's gala last night till really late, so stumbling a little bit today. So we're going to create a model basically using almost every step that we would do out in banking. Probably do some more that they don't do. There's no right answer in this. The whole process is kind of poking and prodding and seeing what you find. In terms of economic terms, we call this a positive process, trying to let the data tell us what it can. There are definitely wrong answers, so I hope you take that away. For those who are good with Python, I provide as much code as I can, but for those who don't want to learn Python, you don't have to worry. We'll talk at a high level and show some nice pictures. So why don't we go ahead and move down? And basically, I'm going to assume nobody here has a background in credit, and I need to present all the basic fundamentals that go into our thought process before actually getting to the modeling. This is supposed to be 3 hours. I have no idea if it's going to take 3 hours, if it's going to take 2 or 4. But at 2 o'clock, we'll take about a 5 to 7 minute break. And then again, at 3 o'clock, we'll take a 5 to 7 minute break, depending on how close we are to finishing. So for those who have not taken the classes, credit is actually very broad, but it breaks down into 4 normal business groups. I mean, there's others than this, but this is where most people work. Consumer credit is probably the biggest, right? I mean, if you think about it, there's 340 million people in the US, and they all need support in one way or another at different points in their lives, whether they're buying a car, a house, or if they just need credit cards, right? I'm pretty sure somebody on this call, on this video, has student loans. So there are more jobs in consumer lending than the other types of credits. But there's also high turnover. So it's kind of a brutal place to be. Commercial credit's where I grew up. That's lending to businesses. I mostly lent to the larger companies. So if you think about it, there are only 24,000 companies in the US that submit to the SEC each year, 10Ks and 10Qs. And then you've got the Russell 6000. Those were my customers, but there's over 13 million businesses in the US. So, and they basically all require banking. Counterparty credit risk is for those who do derivatives like swaps, options, and futures. Securitizations, that's big and coming back, that's where a bank might take a whole bunch of loans and say, I want them off my balance sheet, stick them into a structure, and sell securities based on the cash flows in that structure. So today we're focused on commercial credit, not anything else. So credit is basically just different nuances of these three concepts: probability of default, loss given default, exposure given default, right? So PD, that's obvious. What's the chance somebody's going to default? There's a lot of nuance to that. Like, do you mean what's the chance that they might default in the next year, the next 2 years? Or you can even go more abstract and say, what's the baseline level of default for this type of company? And then add in other like economic factors to make it okay, this company, single A company, that's its baseline. But if I increase unemployment and lower GDP, all of a sudden that single A company will have a very different PD, right? So you could have the macroeconomic focused PD and the non-macroeconomic focused PD. Loss given default, that's literally how much do you think you're going to lose if there is a default. And exposure default is important for things like credit cards, right? How much are they actually going to borrow before they default, right? So we usually combine these to create an expected loss, just multiplying them together. So today we've only got the data to do with PD. Getting data for LGD and EAD is really difficult if you don't work at a bank. So the history is interesting. John Moody started the first rating agency in the US. There were two others in Europe that had started just before him, but he started the first one in 1900, and the first official ratings were published in 1909. Now you can see below that here's the first a list or a summary of the first ratings that he assigned. These were all for railroads. This was back when there were a lot of different railroad companies. They hadn't all been consolidated under standard yet. How many? 1,166. You can see the ratings off to the left, and you can see the constituents that went into it. He broke his ratings into security, which is basically the chance of getting repaid, and saleability, which was how liquid and how easy it would be to sell it without taking a loss. Strangely enough, saleability for him was much more important. It factored more into the ratings than the security, which I thought was funny. So the first ratings weren't really credit ratings. They were kind of liquidity ratings, but whatever. They stayed the same way from 1909 basically till today, though the saleability part fell out. These letters, very high, good, moderate, fair, doubtful, unassigned. Over on the other side is very high, good, moderate, fair, and poor. So there's the source. So the first credit models, though, were developed in the 1970s, and they were developed in consumer finance for mortgage securitizations. There's books written on these guys who did this because they got filthy rich. They were basically bringing a computer to a world that only had abacuses, and so they just made money hand over foot. They would have like no risk at all in the portfolio and get paid like 1,000%. I'm exaggerating, but in the commercial world, the biggest change happened in 1991. When Andy Kimball and Jerry Fons published the very first ever historical default study. You can see the title here, Corporate Bond Defaults and Default Rates, 1970 to 1990. They only had 20 years of data. And they kicked off a change in the way people perceived ratings. The next 10 years were people debating what did these historical default rates mean? I mean, basically, all they did was said, anything that's rated single A, how would that have performed? And they found out that they had default rates associated with it. And all of a sudden, everyone's like, okay, that's what ratings mean. It's the chance of default in the next year, which was not it at all. And we'll get to the subtlety there in just a moment. Here's a version of the default study pulled from the 2022 default study. You've got the ratings off to the side. And it covers, what is that? That's 38 years. So that's a good sample. I didn't provide the counts, but there's many thousands and thousands of companies going into this. What you can see here is if you were rated AAA, like anytime you're rated AAA, the chance of you defaulting in the next year is 0. There's only been one AAA company that ever defaulted within 1 year of having a AAA. You come down a little bit further, down to Baa3 and Ba1, you can see the cutoff between investment grade and spec grade here. So it's someplace around 0.3%. So if the likelihood of you defaulting is more than 0.3% on any given year, you would probably be rated someplace in that realm of Baa3 or Ba1, right? Going even further down to CA and C, the very lower end of the spectrum, literally 1 in 3 companies that have those ratings will default within the year after having that rating. The rest are likely actually to be upgraded from there. So here in 2003, while I was at Moody's, one of my first big jobs was actually to work with senior management to define the ratings for Moody's, and it turned out to be for the industry. This was because Ray McDaniel, who was the president at the time, was a bit embarrassed by some of the defaults that had happened just before I was hired. And he wanted to go out and talk to the investors that use the ratings and say to them, yeah, okay, we think we screwed up here. Sorry, I need to put my phone on do not disturb. There we go. He wanted to go out to the investors and say, okay, this is what the ratings mean, and this is how we're going to improve their assignment going forward. But then he realized he didn't know what ratings meant, right? So that was in 2002 when he hired me to do this job, which tells you that for most of, what is that, almost 100 years, ratings were assigned and people didn't exactly know what they were. The analyst just had a gut feeling. I know this is an A company. I know this is a triple B company. And that was it. So we investigated how ratings were used, how they were assigned, and what potential performance metrics we could use. And we firmly established that they're through the cycle PDs, and we'll talk about that later. We also determined that accuracy ratios were the key performance measure and how well they do. They actually later switched to the average default position. We'll talk about that as well. So in the modeling world, nobody actually was moving towards being more analytic. And that was until the regulators globally made some changes in 2004. So Basel, the Basel Consortium is basically regulators and bank leaders throughout the world. They get together and come up with rules that they hope will be adopted by all countries, and how capital will be determined at each bank, the minimum capital required. So the Basel Accords have been adopted by virtually all countries, first, second, third, developing. Basel II was interesting because what Basel II said was that banks can use their own internal credit models to assign their own capital levels, right? So that's nice because those internal models would be much more focused on the risks that those banks have. And the banks thought that they could reduce the amount of capital that they would be required to hold against a potential failure. The guidelines, especially the US version, which is like 400 pages, outlined best practices for models and ratings. And it still is, I think, one of the best documents for determining best practices. Anytime you see like the business lines trying to move away from those, they're actually making their predictions worse. So it's not clear when scorecards were first used. I remember being at Moody's when we were having a discussion about how S&P had scorecards that they used to tell their investors exactly how the ratings were assigned. That caused a big uproar for us, right, at Moody's. So I think it was 2007, might be 2008, when all of a sudden we started creating our own. And literally it's just sitting down at a table in like committee going, what do we think is important? Oh, total assets is important. Earnings are important. Cash on hand is important. What weights would we put in this? I think this is more important than that. So 10, 20%. It was all just make believe in a certain sense. But that started to change really heavily because of the Basel II models that were being created, right? And they were coming online in 2008, 2009. These were actually statistical models, like we're going to create here. But because the end result looked like the scorecards that were built earlier, all the users just kept calling them scorecards. Just the other day, I was talking with the other lecturer for credit risk analytics, and he's like, why are you calling this a scorecard? It's a statistical model. I'm like, yeah, I've been down this battle before. No, these are scorecards, but they're also statistical models. So if you guys have questions, you can always send something through the chat or just raise your hand. I'm pretty sure we don't have any right now, but don't hesitate. Okay, I'm gonna post the document in chat. I notice we've got like 5 more people. So you can follow along or get ahead. Okay, so this concept, point in time versus through the cycle, one of the most confusing concepts in PDs. First, I'll answer the question. A scorecard is virtually always through the cycle, not point in time. We'll explore point in time models. Oh yeah, this is straight from my class. Later in the semester, we'll actually talk about it a little bit later today. But the reason comes mostly from the regulators. The regulators do not want banks to make their ratings cyclical, right? They don't want all the companies to be downgraded in a downturn and have credit cut off even more. They worried very much that banks would exacerbate downturns and accelerate upturns if ratings were to move too much in time, right? So their definition, they said, it's a long run, average 1-year default rates, capturing the average default experience over a mix of economic conditions, right? So that's confusing. Long run average 1-year default rate, right? So that's not the next year's default rate. It's literally looking at all the years and seeing what, say, a single A rating would have defaulted at. So that should be the appropriate PD. Also, it should not take into account economic conditions, really. As I say, over a mix of economic conditions, right? Especially this thing, including economic downturn conditions, they require that if you don't have enough data to go back behind another recent economic downturn, you'll have to create some somehow or buy some. So the Japanese, who I worked for a long time, had a similar but different one. They said, use a 5-year forecast horizon, but then turn that 5-year PD into a 1-year annualized, like what would be the 1-year rate that if you had it for 5 years would be equivalent to that 5-year forecast horizon. So main considerations for a TTC model: have enough historical data to cover at least one full economic cycle. We have that today. I've got 20 years. When you choose variables, choose more stable variables, right? So if you want to include earnings, don't just use the last quarter earnings. I mean, truth is, using multi-year averages instead is difficult. So we typically use earnings instead, but we find that earnings tend to go down as the market goes down. So using that in a model will not give you new information. It's almost like saying, okay, this company is going to be looking worse because their earnings have gone down. We already knew that because we already knew we were in a downturn. Dead stop. So outside of regulatory requirements, this is a problem with Jupyter Notebooks versus PowerPoint, is there's a lot more text. It's almost like writing a book. I apologize for that. There's more pictures later. Anyway, it makes sense to use TTC ratings for hold to maturity investors because you're not going to be in a situation where you lend to somebody today because they look good, and then tomorrow when prices or anything changes, they look bad. I've got an example of this. In 2016, I was telling my chief credit officer that all of the lending that we were doing to small oil producers was in danger because at the time the oil price was $110. And I basically said, look, historically, prices have moved dramatically about once every 10 years. These ratings were built taking into account too much account of the oil prices. Therefore, if we get an oil shock, all of these guys are going to look a lot worse, and a lot of them are going to go out of business. And we ended up losing hundreds of millions of dollars because of that. We didn't have time to adjust how we assigned our ratings or get out of those relationships. So now the alternative point in time models usually used for pricing or derived from prices, which leads to weird circular reasoning. They often overshoot and then come back and regress to the mean, right? Examples are Moody's EDFs derived from equity prices. They move with the stock prices, or Moody's bond implied ratings. I have to admit, I was the inventor and developer for the bond spread implied ratings. They're very powerful, but they also tend to move a lot. So, okay, I think we're coming close to the end of the preliminaries. Yes. And how far down are we? Oh, okay, we're doing good. The last thing I want to talk about is how do we measure the performance of a model, which is also how do we measure the performance of ratings. You saw I wrote that paper on this. This is something I've killed a lot of neurons for. So the best model that we could have would be one that perfectly separated all obligors into will default and won't default, right? Now, obviously, if we have through the cycle ratings, what are the nuances here? Like, it's hard to perfectly distinguish between will default and won't default if you change the horizon, right? So if you do perfectly on the first year, you may not do perfectly on the second year, right? Because something that didn't default the first year might default the second year. And then you're stuck with this problem of a model that can forecast will default or won't default over a short period of time, but not longer. Of course, we'd only need 2 ratings. Instead, we use 21 ratings typically. And also the regulators have muddled this concept of forecast horizon, which makes all of this difficult. So instead, we use these other performance measures, and I'll show you how it works in a second. We've settled on 3 standard performance measures. There are others, but they have their own issues. So the first one that most people learn about is this thing called the area under the ROC curve, or the AUC. You should know that it's used mainly by statisticians or risk managers in consumer finance. Statisticians love it because it's related to very specific and aged statistical measures. Also, the people in consumer finance like it because in consumer finance, they worry a lot more about lending cutoffs, which allows them to create things called confusion matrices. That said, it's really hard to use AUCs to manage a portfolio. So most everyone else in finance uses a thing called an accuracy ratio. It's similar to the AUC, but it's more interpretable to most risk managers. Surprisingly, mathematically, there's an equation relating the two, and they have a 100% correlation. So using one over the other doesn't really matter. You're going to get the same information. In the end, though, I will say that the easiest way to understand this is called the average default position. I have to admit, I invented this. It's important to know that the ADP and the AUC are exactly the same.
In terms of
so you get the same information from both, just interpreting them is different, right? And here's the equation for AR and AUC. So for the mathematicians in the audience who want to play with this kind of thing, the equivalence between AUC and ADP comes from this relation. This comes from differentiation by parts. So this first double integral is effectively the AUC, right? That D is a distribution of defaults where X goes from 0 to 1. And so that inner integral basically plots out a curve that defines the ROC curve, and the second integral takes the area underneath it. Turns out that if you differentiate by parts, or integrate by parts, I'm sorry, you get this other equation, which is 1 minus the integral of X times the distribution of defaults from 0 to 1. And that can be interpreted as basically the average position of the defaults by the scores. So why don't we go ahead and look at this? Now, let me show you the chart first, all right? And then we'll go back to the Python. I'll when I can, I'll go through Python pretty quickly. So notice this chart goes from 1 to 0, not 0 to 1, because I'm putting all the risky customers to the left, which is feels more familiar to a lot of us. Right. So what I've done is I've lined up all the customers based on a score. The score goes from the riskiest to the safest based on the model. And I plotted all of the customers that defaulted. There's 10,000 customers here. I've added a little bit of noise up and down. That's meaningless. That's just there so you can see what's going on instead of just seeing a bunch of red on the center line. I've added a cutoff. The cutoff can be anywhere. I could put it at 50%. I could put it at 25%. I just put it there just so you have a visual cue that like sometimes you can think, I'm going to have a cutoff and I'm not going to lend below a certain level. And that's actually going to be beneficial because I'm going to avoid all of these customers defaulting. A general rule of thumb is one customer defaulting basically erases the profits for between 4 and 10 other customers, depending on how much you lose. So not lending to all these customers would be good, right? So the average default position would literally be taking every one of these dots, finding out what its position was, right? So this one's at 0.2, this one's at 0.27, this one is at 0.46, I guess, so on and so forth. and then just take the average. There's no integrations. You're just summing by all the positions and dividing by the number of defaults. That's it. It's the easiest thing possible. If all the defaults were all the way up against that number one, you'd have 100% performance measure. If they were all the way to the other end, at the safe end, up against that wall, you'd have a 0, and that would be a pretty poor model. It's actually not a bad model, because then you just take the negative of the scores and reverse it. The worst model you could have is if everything was right here in the middle or spread out evenly across, right? So we like it when the scores we have push things to the ends. So yeah, okay, so let's look at this. I have to admit, I wrote this and then Doug Dwyer improved it for me to make it prettier. Sample size of 10,000, right? We've got this index, which is basically the position, I guess. Yeah, it's a position. Actually, not sure what the quantile is used for. I think that's not used. Yeah, that's weird. Don't know why he put that in there. Then I create some PDs, which basically, oh yeah, okay, that's it. So basically what he's doing is he's effectively creating defaults using the normal distribution such that the default rates down here at the risky side are much higher than those at the safe side. And then this line literally just randomly checks to see whether the company's default, right? So this is a big simulation. The rest of this is just to make a nice pretty plot. I hope you think it's pretty, because I do. I think it's really cool. So yeah. So let's calculate the AUC, or the average position, right? So I calculate the positions. It's basically his index. I do this ROC AUC score. I stick in defaults, which is just 1 or 0, depending on whether they're defaulted and where they're located. I also could have just done a sum product, to be honest. So, and we find out that the average position is 89.94%, right? So yeah, I could believe that. 80, it's around there. So that's good. So now we know that what we want from performance is have all the defaults of the model down at the lower end, right? And that's what we will try to do going forward. So, all right, that was a lot of preliminaries. I thought that would take longer. So, all right. So for a model like this, we need two things. We need data that we're going to use to predict, and we're going to need a list of companies that have failed. Doing a project like this without being at a bank is actually really hard for that first one. Getting data on things like financials is actually pretty easy. There's free sources out there all over the place. I've actually thought it might be a fun thing to create the Columbia defaulted companies list, but I'm pretty sure we get sued by Moody's and S&P, just so we could have a list of them. But let me go ahead and load the defaults. I'm more than happy to share this with anyone who asks. Just email me. They're large files, but we can figure out a way to share them. I mean, the default list is not that large. I think it's a few kilobytes. So I load it, and because the date in this data set's called date, I changed the name to default date so that it doesn't get confused with a later data set. But here's what it looks like. So we've got this thing called CERT, which is what the FDIC uses as an identifier. We have this thing called ID RSSD. I have no idea why the Federal Reserve uses that as their ID, but that is the Federal Reserve ID. I've got the name of the company, the city, state, who bought them, and the date that they defaulted. So if you look at this list now, Heartland Tri-State just defaulted in July. None of us heard about it. But before that, you can see three names that are very familiar to all of us now: First Republic, Signature, and Silicon Valley. And you can see that First Republic was bought by JP Morgan, Signature was bought by Flagstar, and Silicon was bought by First Citizens. Yeah. Now, do I? Yeah. So I'm gonna caveat this. So this data file that comes almost unchanged from the FDIC is a bit capricious. And the reason I know it's capricious is because I lived through the great financial recession. I saw a bunch of banks default. And when I looked for them in the data set, I couldn't find them. The key example I always use is Wachovia. Now, Wachovia had a very similar situation to Silicon Valley Bank, right? So Silicon Valley Bank had some unrealized losses in their portfolio, but actually they were okay, right? They were okay until all of their customers decided that they might be in trouble and took their money out, right? So it was a run on the bank. And that run on the bank led to a run on Signature and led to a run on First Republic. Wachovia had bought some warehouses in Florida and Georgia. And people weren't sure if there was trouble there, but they were concerned there might be. So all of a sudden, all their customers started pulling their money out. So it's basically the same situation as Silicon Valley Bank. But the FDIC didn't mark it as a failure. It marked it as an assisted sale. So there's a lot of defaults that are not in here. I added Wachovia manually. But yeah. So now the financial data comes from the FDIC. Now I'm going to go ahead and go there. I hope you can all see it. So cdr.ffic.gov publishes call reports. Every single bank in the US is required to submit one of these every 3 months. So I have 23 years of quarterly data from the Fed, right? You can look up anyone you want. Yeah, I guess I'll do Truist, if I can spell. And yeah, I can download it. I'm not going to download it. I'm just going to pull up another one and show you what type of data is there, right? Let me go ahead and stop share and then share. If I can find it. This is what it looks like. Kind of ugly, but it's generated. So this is from JP Morgan. This is what they submitted in the first few weeks of 2023 using 12/31 data. And I think this is like, I mean, first off, I probably have close to 200 or 300 of these sitting on my computer because I've used this to figure out what everything is and what's available. So I'm going to go ahead and go in here and just walk through some things just to show you what's here. Let me blow this up. Yeah, there we go. So this is the income statement, right? First thing you're going to see is you got interest income, right? You can see it comes from things like loans, like real estate, commercial. You can see where all the interest is coming from. You've got interest expenses, so interest on deposits. You can see how costly borrowing money from people like us is, right? You've got this thing called non-interest income, which is important. This comes from so they say service charges on deposit accounts, right? So JP Morgan in 2022 earned $5.27 billion from things like overdraft fees or monthly charges. So it's not chump change. There's actually, I think this actually was added to the call reports just a few years ago because of complaints that when interest rates went down and banks could no longer earn interest, they increased all their fees. So the regulators wanted to be able to track that. Down here is non-interest expense. I really like showing this to you because the number one charge here is always, well, yeah, it is always salary and employee benefits, right? So you can see how much they're paying their people. So they're paying $34 billion in 2022. You've got this other non-interest expense. Usually that's IT costs. So your computers and programs. But the fun thing is with that salary and benefits, you can see how many people they actually pay, right? So you can divide how much they're paying in salary and benefits by that 220,271 people and find out how much on average they're paying. And there is a wide differential among banks. I think the cheapest banks, and JP Morgan would be one of them, pay on average like $70,000 or maybe $90,000 now after inflation. But some banks pay upwards of $200,000 and $300,000 to every man, woman, and child. So that's always fun. Jumping down to charge-offs. So okay, first off, definition, charge-off. A bank will, quote, charge off, basically write off, remove from their books loans that they think they're not going to be paid back on, right? And so you can see here, let me find, credit cards are usually pretty big. So they've charged off $3 billion last year on credit cards, right? That they thought they were not going to get repaid for. Yeah, total of $5 billion. That's actually not much for a bank that's $2.5 trillion in size, so that's fine. Could talk about this, but I won't. Just know that this allowance is set aside to protect the bank from potential losses. That's a whole. Actually, it's for. If I have students from my class here, this is something we'll be talking about this coming Tuesday. Let me see. Got the balance sheet, right? So the balance sheet is fun because you can see like how much cash they're holding, securities, how much federal funds that they have sold to others. It looks like JP Morgan actually does all their business in repos. You can see how many loans they have. You see how many trading assets they have. That's useful. How much they have in deposits, right? You can see the types of securities they have. And I think the last thing I'm going to show you is this one on past due and non-accrual. So, okay, anyone who goes past due more than 30 days has to be reported. Now, for those of you who have credit cards and you forget a payment and you manage to make a payment and become current again before 30 days, that's good because the bank does not have to report you. The bank has to report you, then they're also going to turn around and report you to the national credit agencies and affect your scores. So they have to keep track of things that go past due more than 30 days. They typically have to keep track of things that are past due at 90 days and still accruing. JP Morgan is very aggressive. So if you hit 90 days, they're charging you off. That's it. Other banks will work with you and keep you in that column. And then you've got the non-accruals. These are customers that just have stopped paying altogether. So these are things that are useful to know. Let me see if I'm missing anything. Oh yeah, regulatory capital. Yeah, so this is good. Yeah, here we have this concept of common stock, which is reported elsewhere. And usually we have these concepts of tier one capital, right? So tier one capital is common stocks plus retained earnings minus a bunch of non-tangible concepts. Tier two, which is, I think, really only used by larger, more sophisticated banks, is someplace here. Yeah, tier two is missing. Yeah, here it is. Tier two is, instead of going through all the lines, I'll just say tier two are special securities which can be converted to equity if necessary, which is why you're not going to find this being very important for us. One other thing that was interesting here I wanted to show you, AOCI was very important for Silicon Valley Bank. So Silicon Valley Bank, being less than $250 million, did not have to report this. If they were larger and they had to report AOCI as part of their net income, then all the unmarked losses on their treasuries would have had to be reported here, and they would have been reporting losses for years. So that's all here. So you guys all have access to this just by going to cdr.ffiec.gov. It was the very first project I started on when I was learning Python back in 2014. So at this point, I've sunk probably 3,000 or 4,000 hours into trying to understand these things, but you don't need that long. It's just that I was learning as I was going and didn't know anything about banks when I started. So I use this thing called bulk data. I download all the call reports at one time. Let me go ahead and stop sharing and show you. Yeah. I'm going to have to share the whole screen to show you this, I think. Yeah, so bank financials. Going over here to Python scripts, banks, you can see I've created a package called FDIC, one called CDR. So in CDR, I've got all these bulk downloads. You can see them all. They're not that big, but inside of each of them, you'll find that they've got all, for every tab that I just showed you, there is a different text file inside. Right. What was it? So RC, which I just clicked on, looks like this. If I can get away from that Grammarly thing. Just huge amounts of data. And the type of data changes from year to year. So let me show you this. Go ahead and clear this cell. Yeah. So I created the actual function that I use is much longer than this because I deal with some issues in some of the different types of files. But the whole idea here is that I keep everything as is. My computer's fast enough that accessing, reaching into each zip drive, each zip folder, and then reaching into each text file that's in there is pretty easy. And I have a philosophy that says, don't clean data and use a clean data set. instead write code that goes to the original and keeps track of all the potential cleanings that you want to do. So every time I start a new project, I literally do this. I reach inside each of these zip files. So you can see here, I'm going to get a file for a certain date. Sched could be equal to, like, say, RC. And then it's going to open that zip file if it exists. And then it's going to look to see if the file I want is there, right? So if that zip file exists, I'll open it. I'll get the file list of all the files inside of it. And then I will try to open the file that I want. Right? If it's not there, I'll return false. If it is there, I just pull it right in as is. So anyone who wants to follow in my footsteps, this is a good first step, and I'm more than happy to help otherwise. But here's what the financials look like. I pull them in. I sort them, sort values by date, and then by total assets. Ascending equals false and false, which means I'm doing it in reverse order. So instead of starting at 2001, I'm starting at 2022. And I start with the largest bank. So you see JP Morgan Chase, Bank of America, Citibank, Wells Fargo, US Bank, all right? And I have all of these different factors in here. And here's all the information on those. I'm going to create, I'm only going to use year-end data because if I were to use any other quarters, it would lead to me having to do a lot of work to try to create trailing 4-quarter data. In this way, I just get the full year's worth of cumulative information. So I measure the month, and I take annual data being the financials for which month is 12. Yeah. And now I merge it with the defaults from before, right? So pandas merge annual data defaults. Defaults, I'm only keeping the ID and the default date, and I'm matching on the ID. I'm doing left. So I keep everything in annual data and only take the defaults when they exist. I do a trick here where if the default date's missing, I'll put in basically the year 3000. I don't think I'm going to have to worry about fixing all my code. Somebody in 1,000 years will have to worry about it if it still exists. Then I'm going to match it. Oh, I just realized something. I did not add verbiage about how we think about the timing. Okay, I'm going to stop here and just explain something to you. When you create a model, you have to create the model on how you're going to use it. So remember when I said that the JP Morgan used December 31st, 2022 data, but they actually did not submit. Let me go ahead and open this, see if I can find the submission date. Signature page. I'm not going to waste time if I can't find it. But usually there's something here talking about when they actually turn it in. Yeah, it's here someplace. I don't know where it is. So they probably turned it into the Fed in the second half of February, right? So if I were to create a model that started the forecast on December 31st, I wouldn't work because that's not usable information, right? I will not have been able to create a rating until probably March, if not April, right? If I'm doing this automatically, the date that the Fed releases this into the world at the end of February, I can just run my code and use it. But for most banks, they usually take another 2 or 3 months to actually reassign all the ratings because they go through manually. So what I'm doing here is I'm actually creating a period of separated out 3 months and then looking forward to the 15th month, right? So I've still got a year horizon. It's just separated from the statement date by 3 months. And if I have a company, if I have a statement date associated with a default that occurs 3 months to 15 months after the statement date, I'll mark it with a 1, right? So that's that default equals 1. 0 otherwise. And I don't know why I have this here. I can comment that out. The other thing I do is I make sure to get rid of any statements that come after that 3-month horizon. Right. So for any company that defaults, I'll only have one default indicator. And it'll be the first one where there's a default in that 1-year horizon. Right. And you can see I've got 191 defaults. So that's really not that much. I think there's over 36,000 observations in this data set. Right. Now I'm going to do a couple things here. Oh, it's 2:00. I'm sorry. I promised a 5 to 7 minute break. So we're going to take a 5 or 7 minute break now. And we'll start again, basically 2:06, 2:07. And David Romoff, I think you're going to take off, right?
Yes, but thank you. This is awesome. It's a lot of fun. It makes me want to take your class.
Awesome.
Good luck with the rest of the presentation. It's great. Bye-bye, everybody.
Thanks, David. Okay, are we still all here? Awesome, you guys are on great. Thought I would lose more of you. All right, so what have we done? We've created this annual data set, and now we need to start playing with it. So the first thing you would normally do is plot some standard statistics. I'm only going to show one right now, which is the number of defaults each year. And you can see that there's really not that many defaults, except for during the Great Recession. We had 4 years of a lot of them. And that's actually a big weakness of this entire process. Again, I think one way to overcome that is to go and find all the missing defaults in the FDIC databases. But now here's something I normally wouldn't do, but because I'm only putting this together for presentation and the runtime later on was really huge, I started chopping away data that wouldn't necessarily impact the overall process that much. So you see here, I'm just getting rid of anything that comes after 2013, just to remove some data points and make the whole thing run faster. If I was doing this for real, I would not have done that. So most of our defaults fall in 2007, 8, 9, and 10. There were a couple in 2021, and obviously we had 4 this year. So here's the data dictionary for you. Trust, it's whether a bank does any trust business, total interest income, non-interest income, non-interest expense, right? Remember the salaries and benefits, total number of staff, total assets, total cash, total securities, total loans, total deposits. Because all the discussion was about Silicon Valley Bank and its uninsured customers, I put in the total amount of uninsured deposits. Allowance, sorry. Allowance is the total reserve set aside to cover potential future losses, if I can spell. Total charge-offs, it's the total loans charge off during the year. So these are the customers who have already effectively defaulted. We've got the amount of loans that are delinquent between 30 and 89 days. I showed you that. The amount that are greater than 90. So for JP Morgan, they've got 0 because they've charged them all off. They're not holding them on their books. The total amount of non-accruals, right? For those customers who have been charged off, some will continue to make payments, right? Because it's not like they no longer owe the money. They're still going to have collection officers coming after them. So there'll be some recoveries. Total equity, which is the difference between total assets and liabilities. This is basically thought to be a protective layer to protect the deposits. Equity can also have other components like tier 1, which is basically equity minus the non-tangibles. Tier 2, which is a bunch of other types of securities that can be converted if necessary. You got total number of offices. Now, there's an awful lot that I'm not putting in here. I could easily put in a whole bunch of information about like the loan portfolios. So for example, this is, I think this is from 2020? No, 2019. Yeah, so most of this is from 2019. So you see JP Morgan had charge-offs of 0.03% on mortgages, 0.41% on HELOCs. For those who don't know, HELOCs are home equity lines of credit. If you actually have, if your mortgage is worth less than the value of the home, then you've got what's called equity, and banks will give you a credit card backed by that equity, right? So if you end up defaulting on your mortgage, you also end up defaulting on your HELOCs. They go basically hand in hand, but the mortgage gets to recover all of its money first. You got credit cards, autos, personal loans. Now, to see which ones are most risky, you'll notice that mortgages, like for the top 50 banks, averaged over 10 years, only charged off 0.2%. So mortgages are really safe. At the other end, you've got credit cards, which charged off almost 5% on average each year, right? So we as humans are really bad at paying off our credit card bills. So it's very possible that banks that have higher concentrations of credit cards could be riskier. On the other hand, they also get paid something like 15% interest rates. So maybe they're compensated enough that they don't care, right? So things that I haven't included at all in this data set, because if I did, then there would be a huge data set and it would take forever to run, would be like things on portfolio composition, right? Or growth patterns. And we'll actually explore growth patterns later. But here, I mean, specifically that banks that grow too fast are known to be riskier. So the three banks that defaulted this year, First Republic, Silicon Valley, and yes, the other one, they all grew ridiculously fast over the past few years. So they fall right into this bucket. Factor changes is what we'll actually explore later. We'll see how factors change on their way to default. And of course, we could, if we wanted to move from a through the cycle model to a point in time model, which takes into account all this information, we could add macroeconomic variables. I did not try to say Credit Suisse. That's a European bank. But yes, they did fail. I need to go looking for data for Europe. I am coming up here. Where did I put the defaults? Yeah, here we go. Signature, First Republic Signature, and Silicon Valley Bank. Those were the three big ones here in the US. Yeah, I just read that Credit Suisse is charging off a ton of money this year. Billions of dollars. So maybe it's only 2 billion. Still, that's multiple billions. Okay, so the next thing we would do, and actually let me blow this up and say, not that one, this one. Let me put a title in. Factor generation. So factor generation is where you try to actually control what you do with your data, right? Let me go ahead and add 2 bullets to this. Either creating combinations of factors, which you'll see, or normalizing them. Because you need to account for the gross differences in size. Yeah, okay. So let's look at this. I'm creating some new factors here that are very popular. So what is it? Oh yeah, so I got rid of a bad record. Turned out that I had a company that had a bank that had 0 deposits, which was leading to divide by 0 error. But this first one I create, loan to deposits, that's very famous. People look at that all the time. They think that having a number that's high would be indicative of a bank that is too aggressive and has to rely on funding sources other than deposits. Actually, in a lot of cases, they have to buy deposits from other banks. We'll look at the expense ratio, which is weird. We call it the expense ratio, but you see that it's total expenses divided by revenues, right? So as it gets bigger, companies do worse, right? Because they're spending more money on salary and benefits for every dollar of revenue that they take in. So yeah, total interest income plus non-interest income is equal to revenue. And then I get rid of a couple of other issues. Yeah, here's a fun one for those learning Python. Pandas is built on top of NumPy. So when it has an infinity, it uses the np.inf to mark it. I divide the uninsured by deposits. So the ratio is now percentage of all deposits that are uninsured. So that's useful. In this following one, I'm going to take things that are related to the loan book. So that includes total charge-offs, total recoveries, the allowance that's set aside, the delinquencies, and the non-accruals. I'll divide those by loans. So now it's basically a list of the percentage of loans that are charged off or the percentage of loans that are delinquent, right? And then for everything else, I divide it by assets, right? And you'll notice I actually divide loans by assets, right? So why do I do this, right? Why do I normalize everything except for assets? And actually, I should normalize assets in its own way. I do it because the factors themselves grow in size with their banks, right? So if you think about the example, the charge-offs at JP Morgan were $5 billion. $5 billion is larger than the total assets at a lot of the other smaller banks in this data set, right? So if I didn't normalize these things, every single variable here would act like a size variable just simply because they're so highly correlated with total assets in cross-section, right? And that would destroy all the, if you have more than one size variable in a regression with this data, you're going to have problems with multicollinearity, and that'll just cause everything to blow up and you'll get nothing out of it. So it's better to think in terms of proportion of something else. So the reason I said that it would be useful to normalize assets, but I haven't done it, is because, basically because of inflation. The size of a bank in 2001 is so very different than the size of a bank in 2022, right? We've basically, I think, doubled the size of a dollar, right? So a bank could be twice as big in 2022 and yet still be effectively in real dollar terms the same size as it was in 2001. So, but I don't do that here. And it probably has an effect on how important assets are because they aren't that important. Let me go ahead and run this. And then we'll talk about holdout data sets. The last thing I'm going to talk about here before we get into running regressions are holdout data sets, right? I'm going to use one holdout data set, and I'm doing it in a kludgy way, and you'll see how I do it. But if I was doing this in real life, I would use cross-validation. So a holdout data set is useful because I can use it as a test of my regressions, right? So basically, I'll run a whole bunch of regressions and find the regression I like out of all that, and then I'll run it against the test data set and see if it still works. And you'll see what that looks like here soon. The problem is it's actually not an efficient method. One, for a data set with as few defaults as ours, it can be very unstable. And it's also throwing away information, right? Because ultimately, we would like to be able to use all the data in a regression. So normally I would use what's called a cross-validation, right? So it's a little bit hard to explain here. I'll take 30 seconds to try to explain it. For those taking my class, you'll get it in a few weeks. But the whole idea here is that for every regression I run, I'm actually going to run it 5 times. And each time I'm going to hold out a different data set, right? So I'm literally going to run a regression on 80% of the data and then measure its error on the holdout. Then I'm going to put that holdout back in, and I'm going to run on another set of 80% and hold it on that other 20% holdout. I'll end up with 5 runs of the same factors with 5 different holdouts. I'll have run all the data through. And it is, 1, it uses all the data. 2, it's much more stable. And 3, it really affects outliers because the regression that is run and then tested on the outlier will lead to much higher errors than it would have if the outlier was in the regression. So here, let's see, this is how I break the world into training. So I'm going to hold out 15%. I'm importing this thing called random. I could have used NumPy random as well. So the first thing I'm going to do is I'm going to just pull out all the customers at default, right? And I'm going to create a list of random IDs. Right, it's from the list of the IDs. And this is calculating the number that I want to hold out, right? So it's the length of or the number of defaults, 191 times 0.15. I round that number and turn it into an integer. So 0.15 times 191 is probably 29, I bet. So I'm holding out 29, right? Now I'm going to create a new data set, new set of IDs, but these are all the IDs that, and this little squiggle means not, right? So this is going to create a list of all the IDs. I think, it's actually, this is just creating, pulling out all of the data, to be honest. It's pulling out all the data where the ID is not in the default IDs. Right. It made that actually look better. I could have done default. It would have been more easy to read. Same thing though. Then here's all the non-default IDs. And again, I'm going to pull out a whole bunch of non-default IDs randomly. And look at this. I create the test data set, which is from the holdout IDs. Like, so annual data ID is in default IDs plus non-default IDs. This copy is important. So if I do any like changes to the data in test data or train data, it's not going to be looking back to the original data set, because that's a problem with pandas, that if I don't put copy here, I'm getting a slice, and train data and annual data are literally just 2 ways of looking at the same data. So using copy creates a new data set. So the train data is basically anything that is, and it's basically the only difference between train and test is this little squiggle. So this one is taking the holdouts, this one is not taking the holdout data. Right. So this is where we get to look at some fun stuff. So what I'm doing here is I'm literally sorting the data. Yeah, I sort the data by the factor. I'm going to put in non-accruals because that's more visually appealing. Right. And then I'm going to just create this moving average data set where the size of each step is going to be the size of the data divided by 5. And I'm going to keep moving over in steps of 50, right? And I'm going to measure both the average factor and the average default rate. And then I'm going to plot it, right? X is, this is called a list comprehension. You can look that up. People in my class already know it, I think. But yeah, I'll just go ahead and plot this, see what happens. Oh, I should make the data first. There we go. So this is neat, right? So you can see that if non-accruals are pretty low, then there's almost no risk, but then it will increase pretty rapidly, I think up to like 24%, right? So if your non-accruals are in this range, and it looks like there are observations of banks with non-accruals in that range, you've got a pretty high default rate. If we look at delinquent days 30, you get something similar, but not as strong. I think days 90 is just nothing. Yeah, days 90 is basically nothing, just noise. Let's look at equity. That's the big one that the regulators always worry about. And that you can see is very important, right? So above, it looks like about 6.5%, no risk at all. Below 6.5%, if you have not that much equity, your chance of default grows upwards of 33%. 1 in 3 banks with low capital there. All right, tier 1. Tier 1 is similar. I think tier 2, we're going to find out, is actually useless. Yeah. I mean, I have no idea what this peak here is, but there's so many below it that don't have any issues. That's just probably an outlier of some sort. So we've done, total charge-offs. We haven't done all of the loan stuff. Total charge-offs, you can see that the higher is the charge-offs, the more likely a bank is to default. Not much though, only goes up to 12%. So they have better control over what they've already charged off. Let's stick in the allowance, which is basically their, allowance. Really? Let me do that again. Yeah, allowance just looks like charge-offs. That's weird. What other loan-related ones are there? Yeah, print. Data.columns. That way I can look at the list. Oh, trust. First one. That's a fun one. Right? So banks that do not do any trust business have a higher default rate at 11% than those banks that have trust business at about 3%. Oh, wait, 1, 2, 3, 4. That's weird. That's got to be there should only be 2 dots. So that's got to be a function of how the data is sorted. Well, that's funny. I didn't even think about that. Okay, let's try another one. Total interest income. Let's try the income. Noise, nothing there. Let's try non-interest income. I bet you that'll be more important. Yes. So banks that don't, it looks like banks that go negative, if they have negative non-interest income, then they're much riskier, though only up to about 9%. Right. So you can already this is what I love. This just by looking at these charts, you can find neat things. Non-interest expense. I bet you non-interest expense is important, but who knows? And I was wrong. Total staff, let's see. there's somewhat of a relationship there. It seems like there's a higher risk, only up to 4% at the lower levels. Okay, sorry. Cash securities, deposits. Oh, uninsured. So let's look at cash. So this is the amount that a bank holds on its sheets, basically just noise, no relationship. Securities has a relationship. So banks with that trade less default more. Say loans. Banks with a higher percentage of their assets being loans. I mean, this could all just be because smaller banks have fewer securities and basically then more of their portfolio is loans. So what do we do? So we've done deposit. I haven't done deposits or uninsured or expense. So, yeah. So what you can see is those banks that have. So this is deposits divided by loans. So banks that are not lending enough appear to have a higher risk. Is that right? Did I do deposits by loans or by? I did deposits by assets. Right? I divided by deposits by assets, I'm sorry. Yeah, okay. And I'll just do one more expense, the expense ratio. Yeah, and those banks that have higher expense seem weakly to have more risk, but it's not that important. So basically, just by looking through these charts, you've already probably created in your mind a model where you know that equity is important. You know that the quality of your loans is important. There's other things that kind of come into this, but they're weaker. So those would be more like supporting variables. So even before going into this, we already have a feel for what our ultimate model is going to look like, right? But I'm going to do one more thing, and let me go ahead and pull up non-accruals so you can kind of. So this is nonlinear, right? It's kind of like a hockey stick. Logistic regressions and linear regressions both assume that the data is linear, but this is not. So I come down here and I think, where do I put accruals? Yeah, here we go. I basically have this function called smooth non-accruals. So if non-accruals are less than 0.05, I'll set them to 0. And if they're greater than 0.05, I'll just straight line them up on an angle. Yeah, basically I just draw a line that goes like this. Right. So now I'm converting non-accruals into implied PDs and taking into account that nonlinearity. And I do this for charge-offs, right? Here I use 3 lines instead of 2. I do it for equity. I do it for tier 1 allowance. Days 30 happen to have the same curve as allowance. And I also do it for non-accruals, right? And you can see here, I basically, so for days 30, I'm creating a new variable called S for smooth underscore days 30 equals smooth days 30 for all of the observations, right? So you can see that I basically created 1, 2, 3, 4, 5, six smooth variables. And I think here's a list of all the variables I have now. Yeah, you can see 1, 2, 3, 4, 5, 6 smooth versions. So I've got non-accruals and smooth non-accruals. And now I'm going to see how well they perform one by one. So you remember this ROC score, right? So I'm just going to see how well we do in the train data against the factor. For those learning Python, this is a nice format. This little underscore is basically a dummy. If you're working in Jupyter Notebooks, it really doesn't matter because you can't see all your variables. But if you're working in Spider, you're gonna end up, if you put something like for factor in factors, you're gonna have that factor sitting in your variable list forever. So I use these dummies wherever I can. So it's literally going to just take the place of a normal variable, but disappear after you're done with the for loop. So here we go. I'm going to calculate all of the ROC scores for each variable on its own, just to see how good it is. Here, I sort it and then I print it. And again, for to improve the amount of time it takes to run all the regressions necessary, I get rid of some of the factors. So here I'm going to get rid of anything that has an AUC between 35% and 65%. Just chop out the middle and keep the ends. But let's look at what everyone had. So by far the best in terms of single variable capability was non-accruals, right? After that, it was allowance, then equity, then tier 1. Income was important, staff was important, etc. So that's kind of nice. Let me go ahead and just run this again, make sure it's the same thing. Oh, I didn't smooth. Oops. Smooth. There we go. Yeah, slightly different because I chopped out more data. All right. I am not going to run this, but I will talk you through it. Now first off, what I will comment on is I develop in Spider. And when I did things in Spider, I didn't get any issues. But when I pulled that code over here, I got like dozens of errors and warnings. So I was like, it seems to be working fine, and I'm only demonstrating this anyway. I'm just going to turn off all the warnings so it's not showing up as a lot of pink script. So, I mean, truthfully, I couldn't care if I get a convergence warning because that means that regression is probably not good anyway. We use stats models. We could also use scikit-learn. I typically like stats models. Scikit-learn might be a little bit faster, but it doesn't have any bells and whistles that go with it. And I'm going to use this thing called combinations. Let me try to explain combinations down here. If I have a list, 1, 2, 3, 4, and I want all the unique combinations without duplicate, I would like, so if I want every 2-factor combination, I would have 1, 2, 1, 3, 1, 4. Right, so we've got 6 of them. Now, you would think we would probably want 2, 1, 3, 1, but there's no additional information. You'd still be running the same regression, just reversing the variables. So how many are there here? There are, what is it? How many combinations are there? It should be 4 factorial divided by 2 factorial divided by 2 factorial equals 24 divided by 4 divided by 4. No, that doesn't make sense. Oh, divided by 2. Divided by 2 divided by 2 equals 6. Right? If I have 29 variables, that would be huge. I can actually calculate that. Let's see. 29 factorial divided by 2 divided by 2. Oh, wait, no, it wouldn't be divided by 2. It'd be divided by 27 factorial. Yeah, 406 regressions. Sorry. Divided by, yeah, I screwed that up. Divided by 27 factorial. Right. So you can end up with a lot. I mean, let's say I wanted to do 8 factors. That is 4,300,000. So going back up, find it. Oh, that's that. Yeah. So this combinations will get me all the combinations that I stick into it. But you can also see that it can be rather large, right? Factors. Yeah. Go ahead and print. Yeah, so I'm sticking with 16 factors at the end. Right. I think I started with 29. So 16 means that the number of regressions I'm going to have to run is a lot fewer. So let's see how this works. So for the number of factors in the range of 1 through 7, now that actually will do 1, 2, 3, 4, 5, and 6. This 7 is always excluded for some reason. So each time I run through there, I'm going to get all the combinations, right? So 16, so if I have 1 factor, I'm going to have 16. If I have 2 factors, 16 factorial, so 15 divided by 2, 8 times 15, 80 would be 120 combinations, right? And so on. So the number of combinations I'm going to test continues to grow. So for each factor, I'm going to keep track of all my results here. And when I'm done with this inner loop, I'm going to then choose the best result for that number of factors and stick it into winners, right? And you'll see that. I'm not going to run this now. You can see here that even with this reduced data load, it takes 8 minutes to run. When I use all the data and all the factors, it takes a couple hours. And this is a fairly powerful computer. So what does, yeah, why don't I just show you what that looks like. Let's see. Let's do all 3 factors, 3 factor. So here they all are. It's an awful lot of them. So every row has 3 factor names. So 560 of them. All right, coming here. So for every combination, like every row in that list, I'm going to create a data set. So my Y's are always going to be the default indicator, zeros and ones. Training data is literally going to be those 3 fields from training data. And I'm going to add a constant, which just creates a column in X that's called const, and it's just ones. In this part here, I'm literally trying to avoid including factors that are too correlated with each other because it causes problems. So basically, I create a correlation matrix. I go through and I get rid of all the ones in the center diagonal. And if the largest correlation is greater than 0.5, I ignore it. Other than that, I'm actually going to fit a logic model, calculate the AUC. I also do the exact same thing, calculating the AUC on the test data, and then I save it. So I've got the AUC on the test, and a list of the factors, right? And I go through and I do it. For all of those, I sort it by AUC and keep the best result, right? So just so you can see what this looks like. So I'm just pulling in all of the AUCs and the AUC tests and plotting them. So what you can see here is at 1 factor, the in-sample AUC is about 93.7. The test is much lower, under 93. Why are these AUCs so high? It's because we have an awful lot of banks that just look good. Yeah, when you have a low default rate portfolio, you're always going to have high AUCs, right? As I add factors, you can see that the in-sample AUCs continue to go up, right? Actually, the test sample AUCs look like they're going up as well. I've done this a few times and it's not that stable based on the holdout. But usually what ends up happening is the test sample max is at its maximum at 5. Yeah, I think at 5 factors. Is that right? Is that the one I chose? Yes. And so I choose the one that has 5 factors. Right. And so let me go ahead and show you what that regression looks like. So yeah, so I set up the Y and X again. I run the model again and I print it out for you. Close. So this is nice, a pseudo R-squared of about 40%. So it thinks it's doing really well. The factors involved are securities, the smoothed delinquent, tier 2 equity, smoothed equity, which is kind of weird because equity and tier 2 equity I would have thought would be highly correlated. But I think what's happening here is because one of them is still nonlinear and the other is now linearized. They can both be here to capture different aspects. And then non-accruals. And you can see by these z-scores which ones are most important, right? So securities and tier 2 are least important. Delinquencies are slightly more important, but the most important are equity and non-accruals. So we get most of our heavy lifting in this model using smoothed equity, and non-accruals, right? So, so let's see. So these, I'm just printing out all of the winners. So the one-factor model was non-accruals. The two-factor model was smoothed delinquencies and non-accruals. So basically, portfolio quality seems to be much more important than anything else. Not even capital isn't that important. Strangely enough, as you move forward, securities comes in. I have no idea why. That's something I would have to investigate more. Then we get our first equity, right? And finally, now we've got we've got two portfolio qualities, two equities, and one securities in the winning model. If we went further, what would we get? We'd get an income. Now I could have set this up so that instead of just pulling from every factor, I could have actually required there only to be one equity, only one portfolio quality, only one income, but it didn't seem worth it at this quite yet. So I'm just happy that everything looks the way we expected from the pictures we looked at before. So, and now it's 5-3. We're a few minutes ahead. Going to take another 5-minute break. And when we come back, we're going to look at where we would go from this point, from when we've built a basic model. So. All right, and we're back, and you guys stuck around. So, passing over the actual Jupyter notebook. Let's see. And all the pictures that go with it. Let's see if I can give you guys this data. Oh yeah, I can. Awesome. So for everyone who stuck around to this point, you get everything. Right. Yeah. So, okay. So we're here. There's several things we could do. So, I mean, the first thing I will say that normally what I would do at this point is I would actually combine training data and test data into one and re-estimate this model with these factors on the full data set. And then that would be my final model, and that's done, right? But, you know, just because you've built a preliminary model doesn't mean you're done. But again, there's no right thing to do here and no wrong thing. You go into exploration mode. So in my class, I kind of asked my students to look at outliers, right? Specifically, I asked them to look at Silicon Valley Bank and see how well the model did for them. And not surprisingly, given what these factors are, given that Silicon Valley Bank got killed because of their treasury portfolio and their uninsured depositors, none of that shows up here. The model doesn't do very well for Silicon Valley Bank. It actually says that it's a very safe bank. So that shows that even with a model that captures most of the typical types of failures, the model is not going to be able to do perfectly well with everything, right? And so what you would want to do, and I thought about doing this, is to start looking at information like what's the difference between banks that fail, like what are the typical non-accruals for the market? What are the typical non-accruals for defaulting banks, right? So you can look to see how different distressed banks are from non-distressed banks. You can look at outliers. You can look at banks that the model said should fail and didn't fail, and try to figure out why. And you can do vice versa. You can look at the ones that failed that the model didn't say it was going to, that the model didn't say would fail. You could theoretically actually create a new model that tries to capture the banks that the first model did poorly on, right? We're not going to go that route here, simply because I don't think we have that much time. Instead, I started asking the question, do these banks actually look good right up until the point that they fail, or do they start looking bad much longer beforehand? Basically asking the question, is this model actually useful, or is this model actually just telling us what we already effectively know? So here I'm just gonna, the data that I provided is quarterly data, right? So now I'm going to do all the same stuff for that quarterly data that I did for the annual data, right? So here you see I'm creating this new data set called data. I know, generic, but I'm combining the financials with defaults. And I'm doing the exact same thing, which is trying to mark those companies that failed. Now, there's one other thing I have to do here because I've got a 1-year horizon, and now, whereas before with annual data, I was guaranteed I would only see one record flip as default. With quarterly data, 4 of them will flip because 4 of them will see a default within that year horizon. So where did I do this? Yeah, that's it right here. I run code to get rid of all those customers. Only keep the minimum date where I have a default flag. The first time we flip the default, and I call that the minimum default date, right? So here I calculate it, right? And here I enforce it. So every company in this data set now, let me go ahead and run this. Yeah, I ran. So now I've got 206. I'm looking at the entire 206 defaults. I'm looking at the entire timeline as well as every quarter, and I'm restricting the data set to only having defaulters. And I add, yeah, let me also do data. Hopefully this works. I'll pull down 20 rows. No, I'll just do the head. Yeah. Okay. So this is Silicon Valley Bank. You can see it defaulted in March. The date of this observation. Yeah, the first time that we see it in the horizon is for the 2021 12/31 cohort. And I created this relative date index, which is literally just counting back quarter by quarter. So default observation is 0. The quarter before that's -1, before that -2, -3, -4. And you can see how I did that here. Not really going to walk you through on how I did this, but you can probably figure it out on your own afterwards. So, and now I just start plotting, right? So I'm going to put non-accruals here, just so you see it was our strongest variable. And what you see is, and so the chart is quarters prior to default, right? Average value of non-accruals. What you see is that non-accruals, starting about 4 years prior to default, it's 3 years prior to default, sorry, climbs pretty dramatically on average. So we know that something is going on, and you can see it coming from a million miles away. Now, this is where I'm going to say this is only a superficial analysis, because most of these defaults happened during the great financial crisis. So most banks were seeing non-accruals grow. I do not know, without creating some sort of comparison, which is something I will eventually do, I cannot tell you whether these are growing faster than all the rest of the non-defaulting banks. My guess is yes, they are. I just don't know how much, right? Let's that's a good question about the Merton model. Seeing as we predict really well here, I doubt it. But let's hold that to the next section. I just want to show a few more ratios, and then your question fits perfectly with the conclusions. So let me do an equity. And here you see that approximately a little bit more than a year prior to default, capital drops rapidly from about a little over 9% down to just above 7%. Here's a fun one. It's the expense ratio, which wasn't that impressive elsewhere. Looks like this. So banks are actually doing better, doing better, doing better. Then all of a sudden, their costs skyrocket. And you have to wonder why that happens. Starts 2 years prior to default. Doing loans, you also see, here's an interesting thing. The loans typically go up. And here, starting 5 years prior to, you can see the loans on the book increasing until finally they drop off rapidly, like over a course of a little bit less than 2 years. Not exactly sure what's driving that. That's an interesting story. Like, are the banks stopping lending credit, which is most probable? Don't know. So let's look at something that's probably noisy. Days 90 had no predictive power. Oh, but look, days 90 goes up, just not that much. How about days 30? And we see that delinquencies start going up about 3 years prior to default. So all of these things are moving. I will tell you that a lot of this might just be due to the fact that all the defaults happened during the Great Financial Recession. All right. So my next step on this exercise would be to create indices of peer banks at the same times and just see if those peer banks that don't default have the same behavior. And I'm pretty sure they don't. We can actually in the future incorporate factor changes into our modeling. So and that brings us to the end. So we're probably going to finish a little bit early. I can't imagine we go more than like 15 minutes. Go ahead and get rid of this. So Merton model. Would a Merton model be more predictive? No. No, to be absolutely honest, no. If you're talking about a model that's forecasting using equity, they perform really poorly for banks. And they've always been known to perform very poorly for financial companies. Moody's has tried to create a product based on the Merton model for financials and have not gotten wide adoption. The lecturer for the online version of our course spent a lot of time in this area. He's probably a good person to ask, but he, I think, has a certain amount of ownership and defensiveness on the topic. So he'll probably say that they work really well because he's got to, otherwise he spent 20 years wasting his time, which he didn't because risk calc is pretty awesome. So, but there's other models coming up that could be better. So let's talk about it. Yes. Or we could have some static points and some factor growths. Yes, that's exactly the point. So bond implied ratings and CDS implied ratings. So yes, the question was put, what do I think about using CDS spread? Absolutely. Matter of fact, I invented the CDS implied rating model at Moody's. And in our internal research, we found out that they are both more stable than equity implied ratings and more predictive. So the gold standard for predicting defaults is absolutely CDS. The unfortunate thing about CDS is they cover a very small part of the market. So if you want to get past that 3,000 or 4,000 companies, you would need your own model. So, all right. So let's first off, congratulations, you got to this point. We created a model using methods almost identical to how banks do it. I left some things out to simplify exposition, and also to make sure the runtime was pretty short. But I added some things that the banks don't typically do, right? So banks don't very often smooth their data, right? Which is bad because they're leaving a lot of nonlinearity on the floor. They'll have variables that don't perform well simply because they're not linear. And so they don't end up in the final model. The benefit there is the models are simpler, but not as predictive. Without even leaving the current framework, we could add a lot more data from the same source that I came from, like portfolio concentrations, like credit cards. There is some evidence that banks with larger credit card concentrations default more often. We could look at the security portfolio composition, especially given how many companies have actually gone under due to liquidity issues. But we have to be able to go and identify them somehow, or just let the data tell us, I don't know. We can also look at the loan-specific delinquencies and non-accruals. Like I showed you that exists. I would definitely use cross-validation. Anyone who's taken credit risk analytics will see how that works. What are we? We just finished week 4. Next week is week 5. I think it's week 8. So sometime close to the middle or end of October. We could do a lot more smoothing. And instead of doing it in PD space, we could potentially do it in logit space as well. So that would be the natural log of PD divided by 1 minus PD. So we could add macroeconomic variables that would give us more of a point in time model, right? So if your goal is to have the best view over a short period of time, that would be good. And getting back to like an equity-based Merton model, doing it this way would avoid the issues we have with equity models, which is that you would use a security price to imply a PD and then use that PD to imply a security price, right? So that gets circular. We would have something that could stand off as a benchmark without that circularity. There's things I do not like about the results. One, there's not that many defaults and they all come from the same 4 years. So we don't know if this model will actually perform well far away from the great financial recession. Will it do well in the next recession? I do not know. The FDIC hides a lot of their distressed banks. Like I said, they're capricious. I'm actually going to reach out to a guy at the FDIC and start a conversation with them about how they decide, because I would very much like to have a data set that's much more representative. There's a lot of specialty banks in there, like investment banks and foreign banking offices. Like, so an example would be Goldman Sachs's bank is much more of a regular commercial bank now, but when it first started for a few years was very small. And I think they only had like 20 or 50 staff, which was ridiculous, which means that they were getting a lot of support from the investment bank and were considered just as an extension of the investment bank. We don't consider any cross-product terms, right? So a cross-product term would be like, say, if loans and deposits affect each other, and so that having both of them in the regression would be good, but so would maybe having loans times deposits. So you can see if them moving in opposite directions or in the same directions has an effect on the default potential. Unfortunately, for our data set, this very small data set that I created, there would be about 8.8 times 10 to the 30 potential interactions, because it's a factorial process, and that's just way too much. So so as you see, I personally think that to do this right, and I don't think any bank has really done this right, because they don't look at a lot of the things that I've brought up in this conversation. There's a lot of work that still needs to be done to update and clean the data. And especially in terms of finding all the missing bank failures. Even adding 10 to 20 bank failures would give us so much more power. So what other models can we look at, right? So, okay, we can use a hazard rate model. I'm not sure how familiar any of you are with hazard rate models. They became very popular in medicine, especially with things like pandemic propagation. But they also work really well with default studies. So but they are slightly more complex than a logistic model. Oh, and they also became popular in the 80s for consumer debt, because consumers have a prepay option, right? And so hazard rate models allow you to model having multiple types of exits, right? So we've only modeled an exit through default, right? But they were modeling customers who can exit through default and prepay, and just selling off, getting out of the loan. And so these models are more flexible that way. So that's a possibility. I know one bank is moving all of their models over to this, but that's a bank that doesn't have scorecards. They only have stress testing models. So it's a slightly different implementation. I know a lot of you have been trying tree models. People in commercial credit risk analytics will learn how to do tree models. They're actually not hard. They're actually amazingly easy to implement, but they're also really constrained in what they can do. So I would say in the short term, we're going to see more tree models come about, but in the long term, they're going to go away because they're just not flexible in how you can design them. I mean, basically, you can say, I want a tree that has 3 layers and a width of 6, and you're done. Which is why I think the future is going to be neural nets, right? These are the artificial neural nets, the artificial intelligence models that everyone talks about, that you probably all use ChatGPT now. That's one type of neural net. But there's an awful lot more that are made for analyzing data. Yeah, and so the cool thing about neural nets is you don't actually have to find all the interactions. It will find the most important ones almost automatically. Right. So I said that was a huge problem up here, and that problem kind of disappears down here. It's much easier to prepare data for a neural net because a neural net will find the nonlinearities and do its own smoothing just automatically, right? And well, the data that I presented here today is probably insufficient for a full neural net. I've done some experiments, and just a simple off-the-shelf sequential or dense neural net, it can just be as powerful as anything we use here, because I'm not shoving in 5 factors. I'm shoving in all 29 at one time, and it gets to pick and choose what's important and what it wants to use. It can overfit, but that's a topic for another day. Now, the thing that drives me crazy is outside of this data for the banks, getting information for others, things like just general corporates, is really hard, right? I can download the financials for all 24,000 companies that submit to the SEC, but I can't tell you which of those have actually had a default in the past because I don't have a default data set that I can lean on. We usually pull Moody's, but even Moody's has a very limited data set. Though they did just buy a new vendor who seems to have a good mid-market data set that might be good. So anyway, you're all still here. That was it. Thank you for staying around. If you've got questions, I'll stick for a few minutes. If you guys want anything or want help, feel absolutely free to send me an email, whatever you want to work on. All right, I got a request to reshare the Jupyter notebook, so I'll do that one more time. My cursor's not going. There we go. Okay. Yeah. Okay. You should see everything. Oh, I'm sorry. I didn't send that to everybody. Let me do that one more time. I thought I sent that to everybody. Now I will. All right.